for Colossal Cellscapes V1.0. And we'll be using Rhino, Grasshopper, and Unreal. And so I'll introduce Gediminas is an architect and a lecturer based in Sweden. He works as a course coordinator for architecture department of Lund University, runs 2 computation design oriented channels on YouTube, and also is a co-founder of Very Good Architecture Company in Lithuania. His current work and research revolves around real-time environment generation and manipulation techniques, where he's investigating how new emergent technologies can enrich the industry of architecture. This includes, but is not limited to, pathfinding within complex structures, character avatar design, interaction of two participants within the digital realm, representation techniques of metabolous megastructures. So, welcome. We're glad to have you. And right before you start, just want to mention to everyone here, if you want to chat, make sure you switch your chat to say everyone. Otherwise, it will only be to us. You can ask questions also with the Q&A button, which is where all your kind of buttons are. And just a reminder that this webinar is recorded and the recording email will be sent to you to stream after the webinar has finished and Zoom has processed it, which can take up to a day. Just also that if you feel the webinar is too fast for you or you can't keep up, just keep in mind that not everyone learns at the same pace. So, and we have a set amount of information to provide for you. So please, if you can't keep up, just feel free to just watch for now and review back later on the recording. So that's all from me, and we'll hand it over to you.
Super, thanks. And I just wanted to say it's great that you have your master's presentations on YouTube. That's something that I always show to any of my students that are interested.
Oh, that's great.
It's
Thank you.
always lovely to see, what's the output of the school before,
Yeah.
going in and attending the classes.
Yeah.
Right, so I guess we can begin. I will jump right into it. First of all, I would like to share my screen. Just give me a second. As per usual.
All good.
The first hurdle. There we go. Okay, it should be visible, right?
Yep.
Okay, so let's begin. I have prepared a little bit of a lecture / presentation type of a thing just to get warmed up. I'm a bit nervous, and just talking with the slides at the beginning helps out. And also, generally speaking, I just want to contextualize what is it that we will be doing here, what is it that I will be showing here, how does it fit in the whole field of, in this case, architecture, because I am a trained architect. My vocation is architect, and I teach architecture in a university primarily. So all of my research and the things that I do revolves around built environments and built spaces. It does not matter as much if the spaces are digital or if they are physical, if they are physically built. At least it doesn't matter as much to me. And this kind of research that I have been doing for a while now has been anchored mostly on the digital side of things. And only recently have I started making certain moves towards, actually building the damn thing. But about that a little bit later. So as I was, a little bit of a story, as I was studying in the architecture department in Vilnius Arts Academy in Lithuania, we had this workshop by Daniel Köhler, who gave us a basic understanding or basic information about combinatorics and computational design in general. And there, from that workshop, I gathered 3 of my, wouldn't say heroes, but people from whom I started learning very heavily about a different take on architecture, I guess. First one is Gilles Retsin, who deals with combinatorics, which means it's basically all of the elements of a building are accounted for, and they are their own entities that are designed, and you basically design a way of how they fit together. So there's no more column, there's no more staircase element, there's no more floor slab element. Everything is this Lego block, you know, and all you do as you're designing is the relationship between the blocks, between the blocks, yeah. So first one was Gilles Ritson and his combinatorics approach. Second one was Daniel Keller. He is the guy who kind of introduced me to this world of mereology, combinatorics, and so on. And his main focus is mereology. So a science that deals with relationships between the parts and the wholes that they create. Wholes not as in like a pokey hole, no, like hole and as in the whole environment, right? So parts and the wholes that they create. And him asking the question, is it, how do I phrase this? Him asking the question, does only the part influence the whole, or can also the whole influence the part, right? Is it a two-way street? And of course, it is, right? So I'll talk about that a little bit later. And lastly, Jose Sanchez, still can't pronounce, don't know how to pronounce his name, and his approach to aggregations. This is an early project of his, a Bloom Pavilion, where a simple element is grown or connected to copies of itself in a branching way to create something much, much more complex. And the complexity is built into the shape of the element and the way it connects to the copies of itself, right? So it's aggregations, combinatorics, let me go back. Combinatorics, mereology, and aggregations all fit in the same kind of sphere. And that sphere, I would say, discrete element research. Research about architecture that is made out of these discrete elements, bricks, if you will, right? Fancy bricks. But not just that. The relationship between a window and a door is also, you know, two discrete elements in architecture having a relationship to one another. So it goes a little bit deeper. And this is where my research kind of starts. And I start asking the question of, okay, if we have this part, any part, architectural entity, an object, right? And we build a larger structure from it by just simply the motion of copying it and placing it, right, in some way. Then how can the final output influence the part, the form of the part itself, right? So it's not just the part that influences the whole, but it's the whole that influences the part. Remember that the same thing that Daniel Keller raised, the same question that Daniel Keller raised. And I began by creating this very simple Jose Sanchez, you know, branching structure element, and creating an L system, Liebensheimer system, which is literally, you know, you can see it right here. One element branches into two, so basically you copy this element and attach it to the two branches, and so on, right? So it keeps on branching out. And then I forced it to be kind of anchored or locked in between the two skins. So it can only grow, it can't grow everywhere, it can only grow in between the two volumes, and thus whole to part information transfer commenced, right? Meaning that I first designed the envelope and then I populate it with the element, right? So that was like the first test, which led me to thinking of, okay, what's the opposite of that? How do I use the part to influence the the look or the behavior of the whole, right? And in this case, it was just simply changing the element form, right? The way the element connects. And here you can see this stick. Basically, on the left-hand side, we have the Y-shaped element, and then only we have this stick, which does not have any branching behavior, meaning that as it's connecting, you're just creating lines, you know, 2 lines going out, nothing special. But that kind of proves the point that the form of the brick itself has a complete monopoly over the expression of the overall form, the final form, right? Then I replaced it with, okay, what if we have this Y-shaped element that you see in the middle? And of course it grows into this clump, right? Because one branch becomes 2, 2 branches becomes 4, 8, and so on, right? So everything, it always goes by the power of 2. And then I started saying, okay, what if we pair them up and we kind of play with when do we use which element? So the third one, the one on the right-hand side, the structure that you see here, uses both the stick as well as the Y-shaped element to sometimes have a much more linear growth and sometimes have a much more of a branching style growth, right? And this started becoming quite natural, and I could control a little bit more of, you know, how leggy, so to say, the branches are. But there was this issue, and the issue was twofold. First issue was the collisions. Simply the collisions that you encounter when you have this branching structure, meaning that a lot of elements need to be eliminated, right? On the left-hand side, you can see a growth of 9,000 elements with no collisions being eliminated, sorry. No colliding elements, so everything is kind of self-intersecting. And on the right-hand side, you can see the same structure exactly with the same amount of elements, primarily, with collision detection turned on. And then we have 5,460 of these elements kind of cleared out. So that's one. The reason why I call this a problem is because the moment you start removing elements of this branching structure, you're creating a pseudo-chaotic behavior. Because one element that is removed of an exponentially growing structure will ripple throughout the next and next and next generation, meaning that the moment you start removing at least one element, the output of it is unpredictable anymore, right? It's very hard to predict, and you can only predict it by simulating it, right? So that's one issue. The second issue was the structural problems, right? When you have a tree, let me go back one slide. When you have this kind of a tree type of a branching structure, right? Only this starting root element is where everything connects, meaning that structurally, this aggregate works like a clump of hair, right? It's completely, you know, unstructural, and you would need a supporting external structure to actually hold this and have it keep shape. So at that point, I contacted a bunch of people and we worked on it. And the only way of how you can solve this, I'll tell you the secret, I guess. The only way of how you can solve this is by having flexible joints and reconnecting the elements back, the elements that are close to one another, reconnecting them back into these structural loops, right? So having elements that form circular loops. But for that, you would need flexible joints. And I didn't want to go that towards there. So instead, I switched and I promised this lecture is going to be like 10, 15 more minutes, and then we begin with the interesting stuff. I do want it to be contextual, and I want you to understand why do we do the things that we do, and what's the purpose, why. And for the why, you kind of need to know how we got here. So then I took a break, half a year, 1 year, don't remember. And then I came back with a new approach for discrete elements, and that was my round 2, where I started looking into solid shapes, non-planar shapes anymore, solid shapes, and primarily how can you measure the density of a structure while you are morphing the elements themselves in the structure. I know that it's a mouthful, and I know that it's hard to kind of follow, but imagine this. Imagine you have a box, a cube, right? A platonic solid that is a cube, which can stack and completely fill any space. Think of Minecraft, right? You're just completely filling in the space with cubes. Perfect element, always stacks, always, fits. And then you want to change it or morph it from a cube, let's say in this case, from a cube into an octahedron, a rhombus, a three-dimensional rhombus shape, right? And you do so by just moving some not control points, but like mesh points, and then snapping them together to get from a cube into an octahedron. And as you're creating an aggregation of this cube shape that you can see here, this is generation 5, you're measuring, and by the way, I'm not sure, I hope you can see my mouse, probably. I'm showing you the top left, right, top left. As you're morphing from a cube into an octahedron, you're measuring the density of the structure that it has. Also, you're basically just looking if you're getting any freaky or any nice, interesting shapes. And the things that I saw were that at certain angles, you get these quite beautiful, how do I say, crystalline. You get these quite beautiful crystalline structures by morphing from one platonic solid to the other. At certain angles, you get these quite organic looking growths and so on. So there was something there for sure in terms of the research. And I just want to show you in the chat. I will post a link to a video, because showing a video on over a Zoom call is horrible. So instead, I'll just give you a link. Actually, 2 videos. Let's do a Vimeo one first. So please open the chat and go to the Vimeo link. And I'll open it here as well for you.
You just have to switch the thing to everyone.
Sorry?
Just switch the chat to everyone.
I think it's hosts and panelists, right? Oh, okay. I'll switch it to everyone. Yeah?
Yeah.
There we go. Now it should have gone through. Right. So please click the link. It's going to open up this video, and just watch like first 20 seconds or 15 seconds of it. You'll get the idea. Cubes that are morphing into octahedrons. And this is how do I say, uncut. This is unedited, right? So the way it snaps, let me go back here and then quickly show you. The reason why it snaps sometimes from one phase to the other is due to collision detection, right? Certain branches become able to grow, and because of that, the structure just grows at certain angles, right? So cube to octahedron is, there are certain areas that are cool. For example, let me just, give me a second. There we go, this one. There are certain angles that are pretty interesting and pretty cool. You get these crystalline structures. And you can observe, not in this particular crystalline structure, but in others, you can observe the spike in density because suddenly the structure can stack itself much, much better than 1 degree less or 1 degree more, right? So there was for sure something there, and then, you know, I have more of these, the way they morph and the way they kind of construct themselves. So there was for sure something there. I'll give you one more link, and then we continue. While I blab, you can watch the YouTube the YouTube link as well. And I did a lot. I did a lot of these experiments. You can see the graph now on the Zoom screen that you have opened. My presentation. I've done a lot, and I've measured the densities, and you can see that most of the densities at 0% on the left-hand side, they start at 100%, unless I don't start with a cube, you know, my experiment. Most of the times I start with a cube, but sometimes I start with one of the cubes rotated 45 degrees, and then the density immediately drops to below 50%, you know, of space filling. And sometimes you get these interesting spikes and interesting behavior at like 65%, the blue line spikes and so on. And I started looking into those and how do those connect and how do those work. And then I stopped. And I'll show you one more video. And the reason why I stopped is because we never reach 100%. And I think if I reached 100%, it should be some sort of a cool mathematical achievement or something like that, and I would get a medal or something for it. But so clearly, you know, very, very hard to do. And yeah, I've never managed to find a perfectly stacking structure, but I came quite close. I came to there is one that is very, very close to 95% of so it's almost perfectly fitting, but unfortunately I couldn't reach. So the research kind of ends there, right? Because if you don't have 100% space filling structure, it means that you can't form the structural loops, which means that the structure itself requires an additional external like elements, I guess, or connecting tissue, if you will, to be structurally viable. Okay, a lot of nerdy talk, I know. Let me show you a video instead. So what I did instead of that, oh, that's with a sound, okay. One last video. And we're reaching the end of the presentation as well, or the lecture, I guess, itself. Video in the chat, final YouTube video, which actually I should probably also explain what is it that you see. So my research went over to looking at how these structures can follow specific paths, because that would make me be able to actually draw the form, draw the hole, and the part would, the way the part grows would be influenced by the hole, right? And also specifically draw a pattern that is structural, you know, a dome shape or something like that. And this is honestly the closest that I got to something that at least resembles AI, something that makes its own decisions. Right now, it's not that visible, but if we look at how it struggles to reach, you know, when there's a lot of elements in the way, how it struggles to reach the final point, you know, by, well, yep, there we go. It made it. Oh, no, never mind. This is the final one. So there was something natural about the way it grew, and even though these are still non-structural, this approach makes us able to at least drive the load, drive the form of how the loads are distributed through the structure. Meaning, you can make an octopus that has a bunch of legs on the ground, and then because of that make it stable. And also you're eliminating the need for a central core, central element from which everything else grows, right? So that was the end of the experiments. And if you replace it with a library of elements, and you do fitness fit for the best one, you can get a pretty interesting result. So this is where I stopped, because any kind of branching growth is still one-dimensional, meaning that it grows along a line, right? These guys grow along like 4 lines actually. Then if I look at these, clearly, the growth is one-dimensional. It does fill in space because there's a lot of lines, but it's still a one-dimensional thing. It does not grow in a field. It does not envelop a surface, right? So, and the only way of how you can envelop a surface is if you're using a space filling polyhedra when you're doing a branching growth. And I didn't want to do that because that's Minecraft, literally, right? You just choose a cube, you build, anything out of the cubes, and you have yourself, a solution to this problem. But then the reason why I didn't choose, at least the raw voxelized approach, or this cubed polyhedra approach, is because it had so many discontinuities. It's stepped. So meaning that you always deal with a finite resolution that has, all of these nooks and crannies, all of these corners that are not, they don't form a continuous shape. And I wanted it to be continuous. I wanted the form to be completely enclosed in a continuous shape. And the reason for this slide is to explain that you could use, just like Zaha did in her Morpheus hotel, you could use unique elements, and then enclose a unique shape, a complex shape with complex elements, right? That's super easy, and that's, you can do that in Grasshopper. Just download a script from the internet and divide it up, and you're good to go. Of course, rationalizing it is completely another beast in itself, but either way. But it's very expensive. It's very expensive because every element in itself needs to be, manufactured in a, unique way, because it is unique, right? So it has its own parameters and so on, and you need to build a tool, a special tool to manufacture, blah, 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 right? Alternative to that is, the Soviet Union building block thing, where you have a library of elements, this one right here, this one right here, all of the balconies are the same, all of the window openings are the same, blah, blah, blah. You have a library of elements, but the problem with it is that it's very boring, first of all, and very restrictive. Very restrictive in what you can do, because these are just planar slabs, right? Meaning that the moment, if you want to, use something that you see on the right-hand side of the screen to clad something that you see on the left-hand side of the screen, you will have problems. You will have discontinuities, and you will need to create unique elements for every single, joint and every single joining function. And there are architects who try to deal with that. Philip Bloch comes to mind, and so on. But I'm not about that. I'm about finding a library of elements that can clad the skin, the complex forms that Zaha did or any other, you know, architect, mad architects are able to produce in a cheap way, right? So yeah, that's the slide. I already told you what I wanted to say in the slide. Basically taking a blob, you know, a blob that has all of these unique elements and asking the question, what happens if we use prefab stuff on them? First of all, how would the prefabricated elements even look like? What kind of library can you use? Can you have? And the answer to that actually comes from medical industry, which, you know, very, very strange, but actually when you think about it, it makes sense. They have this magnetic resonance, MRA scanners that basically creates a bunch of slices through the human body, right? JPEG images, let's just call them, or BMP, doesn't matter, images, pixels, right? And as you stack them up, you know, in three-dimensional space, you have voxels, because pixel in 3D is a voxel, right? And then the medical industry had the problem of, okay, we have all of these voxels, you know, white voxels when we do X-ray scans or stacked MRI scans. How do we create a mesh from them? How do we create form? And the answer is, you know, on the screen, marching cubes. Basically, at this point, I will open up a website to just talk about it just a tiny bit. But basically, the way marching cubes works is you voxelize a space, just like in Minecraft. You divide up the space. By the way, that was the last slide, so we're almost there. You divide up the space, and you ask which voxels or which, for every voxel, for every cube in that space, for every building block in that space, you ask, are the corners of those cubes, do the corners of those cubes have a point or don't have a point in them? So in this case, for the medical industry, let me go back. For the medical industry, you would be asking, are the pixels in, you know, in this voxel white or black? You know, so, and if they're white, then you register them as populated, and you create, for instance, here, like vertex 3 is populated, and you create a face around it, right? And there's a bunch of math and so on of how it's done, blah, 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 blah. But by the end of it, if I scroll hard enough, okay, never mind. I do need to do this, marching cubes, images, boop, an image. Should have added that to the slides. At the end of the day, all you need is 13 different entities, I guess, 13 different types of the prefabricated voxel to be able to reconstruct any form in a voxelized space. Then me, being an architect, I was just thinking, okay, can these be produced? Can you manufacture them? Can you design them? And this is where we currently are right now. And this is something that I will be showcasing in this webinar, is how can you use this approach of marching cubes to wrap a space or a form around in 13 different elements. So you design these 13 different elements, and then that's all you need to manufacture to be able to produce any kind of a complex form. All right, so that concludes my small lecture or presentation, I guess. Now I have this whole Google Doc file system for you to download, of course. Just give me a second, I'll give you a link to it. I should have prepared the link beforehand, but now I am rushing, I'm jogging, I'm trying my best. There we go. Cellscapes, share. Okay. All right. Copy link. There you go. In the chat, I'll give you a little bit of time to navigate to it and then begin downloading. I hope that it should work clearly. Yeah. So this is everything that we're going to be doing today. 0, lecture 1 are the slides for, the lecture that I just gave you. And now we're going to look at game 0616. While you are downloading the, oops, that is not the game. While you are downloading the Google Drive folder or files from the Google Drive, it shouldn't be that heavy, by the way. It should be pretty, I made it as light as I possibly could. I will just simply run the first folder, one game 0616. Start. I just double click on start game. Alt tab to allow access. And that's how you install bit miners into a bunch of computers. No, it's not. Never mind. Bad joke. If I run level 1, here you will see, and I probably should just give me a second. Mixer. I'll just silence this one so that you don't need to see it. I basically created this environment, and I will of course be showing it to you. I'll be showing you this environment in both Rhino as well as in Unreal Engine. I have created this environment to test out if that custom marching cubes algorithm can even be used to define or to create space. And the answer to that is pretty simply yes, right? Absolutely, it can. The main issue actually was how do you optimize for, how do you generally just be able to show this level or this amount of geometry in one go? And the answer to that is, of course, Unreal Engine. Unreal Engine is great at, specifically Nanite, is great at showcasing very complex forms, simply because of the real-time remeshing that it does. And then I made it into a game. You can see on my top left corner, as I'm climbing up, the percentage is increasing, and the aim is to reach 100%, reach the top of the tower. And it's possible, by the way. I even did, for my YouTube channel, I did a small competition for people who reached the top first. I think first 3 places got like a t-shirt sent to them. Anyway, so that's that, right? And I will not be playing a game in this webinar. I just wanted to show you the end result of this first phase or first part of the webinar, right? The way we get to the end result, to this result, is actually pretty interesting, and I will train you of how you can design your own elements and wrap your own shape, right? Let me create this kind of a elegant loop, I guess, elegant thought loop back to the slide number 2 that I showed you. That was Daniel Keller, Mariology, the pencil that looks like a pencil drawn image, right? And where I talked about part to whole relationship, in this case, the part influences kind of the whole in an aesthetic way for sure, but more importantly, the whole is described by a set of points, a set of voxelized points, and the relationship between the part and the whole, or the whole and the part, is that you only describe, you choose which part to use to wrap the whole around for each individual voxel, I guess, right? So that's it's still there. It's still in the field of combinatorics, in the field of mereology, in the field of aggregations, except that now it's much more of a surface-based approach, much more of a space wrapping approach rather than a linear growth, right? I'll escape out of here. Oh, I can show you level 2 as well. So level 1 takes around 15 minutes to complete. At least, if you know where to go. First time, it's like closer to 30 minutes to complete. Level 2, it took me 8 hours, something like that. And it's, we're already at 2%, seems like it's easy, but I have played, or I have experimented with density a lot in this level 2. And this is a level that no one really saw. I haven't showed it to anyone, simply because it's close to impossible to solve, and you actually need to climb outside of the structure from time to time to be able to progress. And I can kind of go out to show you how it looks like, right? That's the tower. It's actually not even a tower. It's like a cube almost. Sorry, not a cube, but like a elongated building block type of a typology. Anyway, now we quit. Hopefully during this blah blah blah, most of you have managed to download the Google Drive files. I will keep them available for you for the next 2 months or so. So if now you're struggling with getting them downloaded, don't worry. They won't disappear after this webinar is completed, right? So the first thing that we should all do is install the webinar plugins. I do use quite a few plugins in here, and we just right-click on the RAR file, right-click, extract to 3 webinar plugins into their specific folder, double-click, you will have all of these GHA files. Technically speaking, you could just drag them, in Rhino, you open up Grasshopper, give me a second. Or not me, give Rhino a second, I guess. Walter says, wow. Thanks, Walter. So we have this Grasshopper window opened, and we can just simply select all of these and drag and drop them in. Technically, they should load in. I think that, yeah, there shouldn't be any problems, but a clean way of how to do it, especially when you're installing Grasshopper plugins that have DLL files in them, that's for sure that what you need to do is go to, in Grasshopper, go to File, Special Folders, Components folder, File, Special Folders, Components folder. And this is a folder where all of your Grasshopper plugins live. And you just simply get your webinar plugins, select them all, drag and drop them into your components folder. Or in this case, it's actually libraries. It's called libraries here. Under here is called special folders, components folder. I have no idea why the discrepancy between them. right? So after you drag and drop them in, you need to close Grasshopper, close Rhino, and start it again. You know, you need to restart Rhino for the plugins to kick in. And let me just double check what kind of plugins we have. We will have Anemone, Bifocals, Camera Control. Camera Control will not be necessary, sorry for that. Human and Pufferfish. Right, so I'll give you, I guess, a minute. Let me give you less, half a minute, and then we will continue. One more time. File, special folders, components folder. That's under Grasshopper, not under Rhino, right? And then in the file that you, or sorry, the folder that you have downloaded. Let me pop. That's the webinar plugins. You extract it, and you get those into your libraries folder. The reason why I'm kind of giving you time on this is because if you don't do this part, then everything else will fall apart. So it's it's important. It's important, right? Drag and drop in, and then you're good to go. All right. Moving on. So now we need to, I should have not closed my folder. There we go. Okay, now we need to open for CMC. We're blasting through this, right? So not CMC for students. We will open this a little bit later, just for CMC, right? So one is the Rhino file. First open the Rhino file. And second, open the Grasshopper file. Well, okay, let's wait for the Rhino file to not crash during a freaking webinar, please. Oh, come on. That's typical. The reason why I'm showing you this CMC not for students file, I guess, is because notice how it's 13 megabytes, right? And now if I were to show you what's inside of the 13 megabyte file, I think, you know, those of you who work with Rhino wouldn't guess that this is 13 megabytes. And that's the power of blocks, right? Let me actually switch this to Arctic view so that you can see better. You know, that's the power of blocks and block entities. As I mentioned before, the main issue that we have with this approach is that at a certain point, the software cannot keep up, and the software is unable to show the size of the cities or structures that we create, simply because, you know, this element, just from the, you know, by looking at it, I guess it's like 50,000 polygons, something like that, maybe 25, 50,000, right? So two of these is 100,000, let's say. That's 200,000. That's 400. That's gonna be 600, 8, and that's 1,000,000, right? That's 1,000,000 polygons. So in total here we have, that's gonna be 100 million, 200, maybe 300 million, because other types of geometry are a little bit denser than this. You know, for instance, this one. and Rhino is doing fine. And don't forget 13 megabytes. So using blocks for this approach is crucial. That's the only reason why I'm talking about this, so much, is because without blocks, everything crashes, nothing works, it's impossible, right? So you need to use blocks. Even when you're using blocks, at a certain point, the graphics card, just the visual representation in Rhino stops working, and it does not work anymore. I am using a RTX 3080 graphics card, and the limit for this card in Rhino is around 1 billion polygons. Nothing more than 1 billion polygons works. That is one of the reasons why we use Unreal Engine, because I have tested out the maximum of a structure in Unreal Engine, and that was, I don't want to lie, it's either 56 billion polygons or 560 billion. Let's be safe. Let's say it was 56 billion polygons. And the only reason why it was crashing at a larger, how do you say, at larger amounts was because the Excel spreadsheet that we will be using, I'll show you a little bit later, the Excel spreadsheet was getting way too big and it couldn't read the Excel spreadsheet anymore, but it wasn't the meshes. Anyway, so that's the principle of it, and the reason why we're using blocks. Remember, give me a second. Remember this? This. That. This is exactly the same thing, only that I have, oops, sorry. I have now designed every element. I'll give you a quick example of this. We will be modeling out one of these elements together, just for me to show the principle, of how it works, and to make sure that everyone's on the same page in creating your own elements. For instance, this triangle, right? There is one active point here, meaning that the structure chooses to use this triangle, or the script, I guess, chooses to use this triangular element here. And then if I look at this voxel here, that's the element that I have created, shaded, right? We have a triangular loop going around, and everything else that happens inside of the voxel does not really matter, right? So we have free reign to create any shape that we want, as long as the way our shape touches the surface of the voxel is exactly as described in the the marching cubes algorithm sheet, that graphic. And then if I show you how that corner element, this element in particular, works, for example, here, there it is, right? There was a single point there, and it was just creating this, it was just wrapping that point around with these elements. Easy peasy, right? And they meet together perfectly, simply because we didn't mess with the perimeter of it. That's the rule. That's the only rule that you need to follow, right? Now, let's open up CMC for students. You don't need to open up CMC.grasshopper. That's fine. We will immediately jump to CMC for students. That's going to be more valuable. So let's open up CMC for students Rhino file. It should be much less heavy. Just crashing all the time. Not crashing, but I'm scared. I'm scared for the Unreal Engine portion of this. If Unreal Engine is going to be this slow in loading things, yikes. And I guess this could be our first break as well, as we are loading in both Rhino files and Grasshopper files. It seems like I will need to kill this. What the hell? Wait, let's think if we need a break or not. Up. Yeah, I just load it in. Okay, that was weird. We don't need a break. We continue. We will do a break in just a little bit, but I've been at it for 1 hour, so I guess 25 minutes more, and then we will have a break. So load in the Rhino file, load in the Grasshopper file. It generates messages. Okay, I do want to see them. That's fine. That's fine. Don't worry about the messages. You're good to go. Right? We have ourselves a Grasshopper script. There is a reason why I will not be showing you follow after me type of a tutorial for the Grasshopper script. It's simply because I had a small group of my students in the university to whom I was trying to teach the script, and it took a semester, doing the script does not take a semester, but being able to completely explain and teach the script took a semester. So instead here I will guide you through the key points of the Grasshopper script, try to explain them, and I'll show you how to use it as a tool, right? Because you don't need to change anything in the script. You just need to use it to be able to use it as a tool. And the thing that you do as a designer is actually design the elements themselves rather than designing, some node system here. And just to be clear, here that doesn't look that bad, but notice that here we have some clusters, and you know what clusters are. If you don't, I can double click this. Clusters are, groups of stuff. A script in a script, I guess. I don't want to save any changes. Okay. I'll give you a minute to catch up. Not to say that you haven't caught up with all of my blabbing. And then we'll continue. All right. Let me slowly ease you into the files, the tools that you have. First of all, only Rhino. Only in Rhino, I want to talk about the library that you have here and the layer system that I have created for you. You have, initially what you have is two layers. One, CA points, that's cellular automata points. This layer should be empty. It is. If I show, nothing's, okay, perfect. This layer is empty, right? We will be creating CA points, cellular automata points a little bit later, but we already have a layer for it. And then we have the guide. The guide is this library right here. You should not move the guide. You should not delete anything from the guide. You should not even look at the guide for prolonged periods of time. If you do so, it's going to break and nothing will work. Welcome to research. So the way the guide works is you have the cage. The cage is literally just a frame of a voxel, right? In which the elements live. It's curves, it's just lines, nothing special. Then you have the guide geometry. The guide geometry, the only thing that you care about is this line or these edges that touch the sides of the box, right? The sides of, because those are the connections. That's where your elements will connect to one another, right? Very important, right? Everything else that's happening inside, you know, it's up to you to decide, design, right? Then we have guide points. These guys are basically showing us which, give me a second, which points are populated in a voxel space. And I will talk about them a little bit later, but you can see that, you know, when you have one point on a voxel, it draws a triangle. If you have 2 points of a voxel, it draws this rectangle. Those 2 points can also be, for instance, let me do a point here. Oh, 1 second. A point here and a point here. Those 2 points can also be here, but then that means that the rectangle that is drawn is going to follow the alignment of those points. I have way too many snaps turned on. Just give me a second. There we go. Should work. There we go. Mid. Okay. So if you have 2 points horizontally, the rectangle reacts to them like so. If you have 2 points vertically, rectangle will be placed here. Hopefully that makes sense, right? And so on. You know, diagonal 2 points, 3 points, make this kind of a shape, blah, blah, blah. All of the possible variations are here. All of the possible variation permutations are here as well, and they will be accounted for. Actually, that cluster that I showed you accounts for the variation permutations, right? Meaning all of the possible ways of how, you know, this single point can be placed in a voxel. These 2 points can be placed in the voxel, are solved here. And then from those permutations you choose, the script chooses the correct element, right, to place in one particular voxel. But now I'm getting ahead of myself. First thing that we need to do is understand what is the output that this script will give us. And the output is going to be place block. It's going to be placing blocks for us. The question is, what kind of blocks? You know, do we have any blocks here? If I type in block manager in Grasshopper, in Rhino, this is empty. There's no blocks. Well, that's because we haven't created any elements. All we have is just the guide, cage, guide geometry, guide points, and guide text, right? We don't have the actual geometry to place. To actually be able to run this, you need to have 14 different blocks. I'll go through this very quickly. Block 1, block 2, 3, block 4, block 5, blah, 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 block 14, right? You need 14 different blocks, and all of their names should be element, E-L, 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 like that, 14, right? I can show you the, you know, desired block naming that comes out from here, from this generator right here, EL1, EL2, EL3 until EL14. It's basically going to choose the correct block according to how it fits. I know that we're going backwards right now, but in my experience, this is the best way of how to teach this method of geometry creation. So we need names we need to create 14 blocks that have names from EL1 until EL14. Let's do that. And since we don't have any geometries right now, I will do a bad thing and I will simply use our guide geo layer. You know, I'll use these geometries that we have here. And give me a second, I'm thinking. Yes, that is what we're going to do. All right, so for guide geo layer, I will unlock it, first of all, important, unlock, right, under layer manager. Select the first element and type in block. Hit enter. It's going to ask you for where is the block base point? You know, where is the origin of the block? I have made a script in a way that the origin should always be at 0. So you just type in 0 and hit enter. And then you give it a name, EL1. Element 1, EL1, hit OK. Great, now we have element 1 set as a block. Perfect. Now I select the second one, block 0, EL2. Guess what we're going to be doing now? Yep, block 0, EL3. Don't forget the caps lock. Block 0, EL4. I'll speed up until 6. Block 0, EL5. Okay, and 6 has 2 elements, so make sure to select both of them. Not elements, but parts. Element number 6 has 2 parts, so select both of them, enter base point 0, EL6. 7 has 4 parts, select all of them, block 0, and so on, right? So we go through this together. Do you even know how many times, oops, that's 7, my bad, EL9, how many times I have done this, this naming, specifically naming of the blocks. I have, oops, that needs to be 0, 11, EL11. I dream of it. 0, EL12, almost there. 0, EL13. Okay. I will give you a minute, not a minute, less, 30 seconds, and we continue. All right. If you type in block manager, you should see 14 different blocks, right? So they already live here. Lock the guide geometry layer so that you don't accidentally select them anymore. Oh, wait a minute. Why can I still select it? Oh, that's because, wait, I can't click on it. Rhino, are you bugging out again? I can sometimes select it. I can't click on it, but I can drag around it. But I can drag around it from left to right to select it. But I can't drag around it from right to left to select it. Oh, Rhino. Okay. Okay. That's fine. Weird stuff. Anyway, we have our 14 blocks, right? Back in Grasshopper, it behaves that way for you. Okay, that's fine. Rhino being Rhino, that's okay. As long as it's not crashing, it's we're happy. We're happy. So now we need to check if the script works or not. Generally speaking, right? If it can fetch the 14 blocks and choose them in a correct way to stack a form with. And for that, we need to create a voxel grid. Let's start simple. Let's start with a single point. The point, one important thing, important note, there needs to be at least one point that is at 0, 0, 0 coordinate, right? At the start of the world. And all of the other points, unless I fixed it, I don't remember if I fixed it, give me a second. Subtraction goes into negative, creates a box array, chooses closest point. Just to be safe, let's do it the old way. All of the points that we create should be in the positive x and positive y. They shouldn't be in the negatives. I don't remember if I fixed this bug or not, so let's just be safe. Work in this quadrant. So let's just place a single point at 0, 0, 0. And let's just move it into our CA points. Select objects. Nope, change object layer into our CA points layer, right? 0, 0, 0. Now let's go to the start of our script and reference it in. There's a point that is waiting for it to be referenced, right? So right click on the node, set one point, click on the little point right here, and something happened really quickly. The thing that happened, I can guide you through this. It creates a bounding box around a point, which is literally nothing, that there's, the bounding box is empty. And with a little bit of math, it creates a box array around the bounding box. Even if it's empty, it still creates a box array around the point. So you can see we have our center point right here in the middle, and then it voxelizes the space around it. If we had 2 points, it would voxelize the space around those 2 points in particular, right? And then with a little bit of anemone shenanigans, it goes through each of those boxes, and you don't need to do this. Please don't do this. I will do it for you. At first generation of the loop, if I reset this, it starts at voxel number 1 right here. Out of all of these boxes, it starts with this one, right? And it goes through and it checks for this box which point is, which corner of the box is filled with a point, or multiple points, which corners, I guess, are filled with points, right? And it gives us this, not matrix, but like a list of, for every corner of the box, there's na, 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 yeah, na. The yeah means that there's one point on the corner, right? Then it goes through all of these different, not variations, but how do I explain? Types, typology, types, different types of voxels that you see here in the library. If I were to show you this point right here, that's the first point. Here I have referenced 2 points, and the output that I get from them are all permutations, all possible permutations of That's just 1 point permutation. Okay, never mind. Are we not? Oh yeah, okay, sorry. My apologies. We're actually, I optimized it so that it's harder to visually see, but you can see it in the number list. So all possible permutations of all corners of the box being checked for points. So I guess the easiest example would be, or easiest way to show it would be with the when only a single corner of the box is populated with a point. Here my permutations look like 1 0 0 0 0 0. So the point is in the first corner, then 0 1 0 0 0 0 0 0 0 1 0. You know, so we have all of the possible corners of the box, you know, checked. And with it, it also gives us information of how it should be rotated, you know, so which point on the corner is checked also kind of carries over the information of how this element should be rotated to actually match with that corner. So that's important. And if I were to look at, for example, element number 6 right here, that's like 4 corner points, right? So we have all of the permutations of 4 corner points, those particular 4 corner points being checked. And we have 24 permutations in total, right? So now you know 4 corner points like that can be rotated uniquely 24 times in 24 different positions. That's a lot of positions. And yes, it does check for duplicates as well. Anyway, I expanded on it a little bit too much. So it basically looks for all of the permutations of all of the possible, all of the library of elements, all of the possible permutations, it checks with which does this match up. And it matches up, of course, with element 1, right, with this one. So because of that, this wire is the only wire that is active. All other wires are not active because they don't match up, right? And then it kind of spits through right here into the I can show you the vector display right here. And it basically just moves this element to here and rotates it properly. It doesn't really move and rotate the element, it just records of how an element should be moved and rotated. Because the next thing that we do is actually just record the name of the element, not the element itself. This makes it much more, much faster in computational sense, right? So the final output that we get after only this single voxel has been calculated here, that goes into the place block, it has element 1, you know, that's the name, and it gets transform, which is compound transformation of 4 different things. I believe it's going to be, give me a second. Is that a transform? Nah, that's just a very heavy cleaning of the data tree. No, I don't. That's going to be where the transforms are calculated. Yeah, you can see here rotation around 1, 2, 3 planes, and then there's also going to be a mirror somewhere, or just a move. Sorry, it's just a move, it's not a mirror. So you have rotate around X, rotate around Y, rotate around Z, and move to position. Those are the 4 transformations that the compound transform is made out of, right? Back in here, right, we have how the block should be moved, that's the X form, and what's the name of the block, that's element 1. If I click the button here, voila, a triangle has been added. That's a lot of work for adding a triangle, right? Let me actually unlock the damn geometry layer so that I can, or actually let's not unlock it, let's just Control Z in Rhino. Control Z in Rhino. Control, oh, there we go. And let's instead let it run for, you know, all the possible, all the necessary voxels. So I'm going to reconnect it here. Don't forget to also always, when you change something, click the reset button for the loop so that it recalculates, or else is gonna remember the past blocks and it's gonna be all a mess, right? Now if I click the button to place block, voila, our point has been successfully wrapped with element 1. Okay, that's, you know, a lot of work for 8 triangles to be added. But now with this setup complete, all we need to do is construct a point cloud that you want to be wrapped, right? And that starts becoming quite fun. One rule is that we are working with a voxel structure, right? We are working with a voxel structure, meaning if I were to make a copy of this point and just place it randomly here, and then I select both of these points and I say set multiple points, you know, run this, the box array kind of works, you know, it kind of wraps around the points, sure. But then if I press place block, it only places the blocks around my first point, and it doesn't place the block around the second point. What the hell? Why? Well, the reason for that is because this block, or sorry, this point never touches any of the corners or of any of the voxel, meaning that it gets discarded. So there are rules of how these points should be placed. And the rules are, you can only use steps of the voxel size. And the voxel size you can measure by just, you know, either measuring the voxel size here, distance from here to here, 10 centimeters, sure. Or you can just take this. I think it should be, yeah, here. And you can just look at the number here. That's set to 10, sure, 10. Like that, 10. There we go. Now we have 2 points that are 10 centimeters apart. Right click, set multiple. The reason why I'm using 10 centimeters is centimeters in particular is because Unreal Engine uses centimeters as its default, whatchamacallit, unit, as its default unit. Okay, let me reset. Don't forget the reset button, always reset. Place block button, voila. Now it wraps the 2 points around with the blocks. Let's do one more. I'll copy one of the points up by 10. So now we'll have 3 points. Set multiple. Reset. Had to count a little bit longer. And now we are wrapping around 3 points. Cool. Starting to get cool. The problem is that these 3 points, it's literally as if we're wrapping around 3 pixels. You know, in that medical MRI scan example, that would be exactly the same thing as us wrapping 3 pixels around. So for you to have something very complex, you need a lot of points. And for that, you need a lot of elements. And for that, stuff starts crashing. You need Unreal Engine. So now we are going to have a clean number would be 17-minute break. So we will meet up at 50 past, right? 50 past, yeah, and we will continue. I suggest that you just play around with the points to understand how they work, and I'll show you a few more examples, of course, once we're done. But let's continue 15, sorry, yeah, in 17 minutes, probably 16 by now, right? Always reset, by the way. Always reset. Oh no, it's becoming phallic. Abort. Oh no. Since I am bored, I will be showing you one little trick, I guess, or one way of how you can work with this, and that I found. This is like not part of the webinar, but I think it might be useful to some, or at least interesting to some. If I were, and yeah, while people are all doing a toilet break and so on, I'm just gonna show it. Let me delete all of those. In Grasshopper, I'll go fast with this. In Grasshopper, if I were to create a point, a single point, or rather construct point, right? And then I would box array it. Box array it. The cell should be a domain box. That is 10 by 10 by 10. I'm basically just making an array of points, right? And in X direction, let's say we have a decent amount, like 50 by 50 by 50, right? Like this block of points, right? And then just so that I don't need to look at them, I will just create a bounding box for them. Not per object, union box. And then I will just extract a wireframe, brep wireframe. There we go. Now we can hide everything except the wireframe box. Okay. And then I can create, let's say, let's do a sphere real quick. Wherever, here, doesn't matter. Let's do a sphere. And then I will reference it in as a brep. I will actually mesh it, mesh brep as a speed, settings speed, so that it's the checks are going to go faster. That does not look like it's for speed. Anyway, doesn't matter. So we mesh the sphere and we check whether or not points are in mesh. Mesh inclusion. Test a point for mesh inclusion, right? For each point, we check if they are inside of the mesh or not, right? And we get the answer true or false, for each point, and then we can cull pattern. We can cull the whole list of points with only the ones that are inside of the mesh, right? So we only get the voxels that are inside. And then I simply just take those points and connect them to the point input here. And now I can, the hell is it doing? Oh no. Oh no. Yeah, that's what I forgot. We need to cancel. Apologies. We need to actually disconnect this, and the sphere, of course, needs to be closer to our 0, 0, 0 point, and also to this whole list. We always need to have at least one point at the beginning, as I said, So I'll construct another point. It's a small, yeah, it's, this part is not elegant, but it is what it is. Merge our whole list of points that are inside of the sphere, as you can see here, and our single point that is there. Those are now merged. Slap on the, make sure that it's all flattened. The output is flattened. And now if I were to reset, and look at the box array of this, this is all of the voxels that is going to go through. And in earlier stages of this, this would take a very long time because it would automatically place a shape or one of these voxels for every voxel that it evaluates. But in this case, it does not, right? And I will just let it run for a while. I think we're at level 2. And you can see even since I enabled the vector display here, every time that it grabs one of these elements, when it's actually using one of these elements, it shows the vector for movement. So you can see which element is grabbed at which point, at which stage, I guess, right, for which voxel. So I'll let it run just a little bit more. This is, not, how do I say, necessary, I guess, but it's just fun. Because you can drive it with a sphere or any shape that you want, so you can model out a duck and you can wrap a duck around with these elements if you wish, right? By just simply doing this this script right here. I'll for those of you who want to do a print screen of it, there we go. Together with my explanation, this should work. And we still have 4 minutes left until the end of the break. I just wanted to show you, this kind of bonus thing that it's not necessarily you working with the points individually, but you can also, do some Grasshopper shenanigans to, interpolate any kind of form with the points. How many? Okay, 2,700 in total, 3,000. Okay, I'll let it go until it finishes. And I'm also going to be showing this to kind of not prove a point, but to also showcase one important aspect of this. Okay, it's done. Let me hide the sphere. And let's just bake out the elements. Boop. Ta-da. The sphere was a little bit off from this side. Actually, I'm interested. Show selected. Yeah, okay. Barely those 2 points catched, so the sphere could be made here, but hey, that looks pretty decent. Anyway, so we have ourselves a sphere, and you might think that, oh, is it solid? Did it place elements inside of the sphere? No, it didn't. If I were to unlock that, let me just delete half of these, show you the inside. It's hollow. And the reason why, it's not just hollow, it's if I were to check here with points, it's full of points. The reason why I didn't place any elements is because there is a rule in the marching cubes algorithm, and the rule is an inverse if there are more than 4 corners of the box that are of the voxel that are used, then an inverse is calculated, meaning that if all of these elements, all of the points on the voxel are used for element 0, which is empty, then it's going to calculate it as if no points are used. If 7 corner points are used for element 1, then it's going to calculate it, as if only one corner point is used. As long as you're going beyond the half mark of how many points there are, it's going to calculate the inverse. You'll notice that there's not a single voxel here that deals with 5 points, and that's because you don't need to, right? You do the inverse and you just place the element, for any 7-sided or 7-corner voxel, you just use element 1. Hope that makes sense. So because of that, since all of the voxels here are fully enclosed by points, all of the corner points are used by the points, they're just empty. They just become empty. Right? All right, let's move on. Let's move on to, actually give me just 1 second. Oh, the break is over. Welcome back. I was just showing quick way of how you can wrap any kind of geometry around with the points. Not really that important for this webinar, but just wanted to add a little bit of something, a little bit extra. Let me just quickly open CMC to Unreal Engine Rhino file here. Just want to check if stuff that I have here is sufficient or not. Yeah, that's decent. I will be giving you all of my elements as well. And then just quick Grasshopper check. Apologies for this technical, not even technical issue, just checking if we should stay on the CMC for students or should we move on to CMC2 Unreal Engine files that we have. Oh, it's immediately doing something. Stop, cancel. If you want to cancel the calculation, you can go to loop start, right click on it. No, yeah, right click on it and choose enabled and you just disable it, right? And it stops calculating. Reset, well, reset won't work. Okay, for now that all is good, that's fine. Again, apologies, should have checked this before. Yeah, we have all of the elements here that are set up, but these are my designs. I want you to create your own design for at least one of the elements. So let's actually stay on the CMC students, CMC for students file for now, just for a little bit. And let's just quickly create element, I don't know, how much time do we have? 2 hours have passed, so that means there's 3 hours remaining. We are right on time with what I expect. Element 2. Element 1 is too fast, would be too fast. Element 2, I think, is going to be a little bit more of a challenge, but less of a challenge compared to element 9 in terms of designing. So let's make it, let's make something cool from element 2. The first thing that I do is actually, let's lock it, and I create a new layer. New layer, call it elements, just elements. Double click on it, make it active, and begin modeling in it. So the first thing that I always decide upon is the thickness of the elements that I'm going to have. I don't want my elements to be paper thin, right? I want them to have girth, thickness. So in this case, since we're dealing with centimeters, and I know that from here to here, this is going to be 10 centimeters, I'm going to guess maybe 1 centimeter of thickness should be good, should be fine. You can do like half. And you don't really create a surface and offset it because that would result in a very messy seam, a very messed up seam. Instead, you work with points. I like points, as you probably have guessed. And we just create a point for every corner of our shape, like that. So 4 points in total on every corner. And for example, for this edge, I will just copy my point up by 0.5 and copy it down by minus 0.5. So I'm only allowed to slide the points along the edge, right? I'm not allowed to do any shenanigans where they leave the edge. And hopefully this will make sense once we finalize this. And perhaps I will even do 2 elements just to show the connections between them, right? So I will do so for the next one as well, minus 0.5 and then 0.5. Like that. This one, 0.5, oops, minus 1. The offset along the edges on 0.5 centimeters. 0.5 minus 1. There we go. So you should have, if I select this, you should have something like that. In total, 8 points, right? That are still not leaving the edge. Very important. Then you can choose to use either solid modeling techniques, or you can use sub-D modeling techniques, mesh modeling techniques. Really doesn't matter what you use. I personally like using sub-D modeling techniques simply because they can be either hard surface or soft surface, whatever I want, right? It's much when you're doing conceptual design, it's very malleable, right? It works like almost as if you're working with clay. I enjoy modeling with sub-D quite a bit. When dealing with actual, architectural design for manufacturing, for building, of course, you jump to solids, you jump to NURBS, but for conceptual work, sub-D is the best. Also, generally speaking, landscape design, sub-D, always very good. Anyway, so in terms of sub-D, we go to sub-D tools, and we choose here, create a single sub-D face. I believe if you just type in 3D face, and you can click on output to choose sub-D, that is going to do exactly the same thing as the icon here. And then I click here 4 times to create the top surface. It's easier for me, and I'll flip it so that you are not confused. It's easier for me to first make the sub-D and then to show you, what is it that I'm doing. And I'll do one more for the bottom surface. 1, 2, 3, 4. There we go. Now we have 2 sub-D shapes. You can toggle, those of you who are not familiar with sub-D, you can toggle between soft body preview and hard surface preview of the sub-D by pressing the tab button below the escape key. Tab. Right? Now we need to connect these 2 layers together, and we can do so by using the bridge command. Bridge, first line, enter, second line, enter. Segments 1, join, yes. Hit OK. Again, bridge, first line, enter, second line, enter, yes. Faster way to bridge things is if you hold Control Shift, and you click on the 2 edges, you can bridge them immediately. without, selecting the first edge and the second edge. You can just Control Shift, select both edges, bridge, okay. Congratulations, you have created a blob that can also be a rectangle. Now for the shape, the issue with sub-D is that you don't want it to smooth too much in, around here, around this, apologies. You don't want the sub-D to smooth out too much. You want it to hold the corners a little bit better. And for that, I will be creating more edges on it. So at this point, we don't need a guide anymore. I will hide the guide layer. We don't need the points anymore. I will PT, select points and delete them. And I will just be working with this shape to make it as, the best that it can be in terms of holding the form and so on. I can't stress this enough. You don't need to do sub-D modeling for this step. You can create any kind of shape that you want in this voxel for this element, and it's going to work. The only restriction is following the perimeter. You just need to follow the perimeter. As long as you follow the perimeter, you're good. You're fine. It's gonna work. So with that being said, I will be showcasing a sub-D workflow. So I will be using insert edge, and I will select the left-hand side perimeter of my edges, and then I'll just pray that all of them insert in the correct side towards the correct side, and they should, because there's nowhere else for them to go, right? So insert edge, offset mode, proportional. And then I just drag my mouse until I hit the middle point, click and release. There we go. Let me see. Yeah, that looks fine. Right? And then I will create one more by selecting the top perimeter, like so. Control Shift, click, 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 click. The top perimeter. Insert edge. And now it shits the bed. Okay, so when it shits the bed like so, you can see that some of the edges are being inserted to one direction, others are being inserted to another direction. That's not a problem. All you need to do is insert them separately. So insert edge for these two edges first, drag them to the middle, insert edge for the side one. Ew. The hell is that? Okay, offset mode, absolute. Or rather, sorry, let's not do the side ones first. Sorry, if you did it, Control Z. The top ones, insert edge, snap them to the middle. The back ones, also in the top, insert edge, snap them to the middle. And can we just delete the sides? Control Shift, select the both of the sides, delete them, and just use bridge, right? So click, select the 2 lines on the top, 2 lines at the bottom, edges. Type in bridge, they bridge nicely. Same thing here, 2 lines in the top, 2 lines in the bottom, bridge, bridges nicely. Tab, we have ourselves still a damp pillow, but now we have these loops, these edge loops that we can use to make it much, much stiffer. That's the reason why we use them, right? So now I will double click on my vertical edge loop, central vertical edge loop, double click on it, Control Shift, double click on the vertical edge loop, select it, and I'll type in bevel. Bevel. I'll choose segments 1. I'll just drag it to very close to the ends, I guess, of the element, just like that. Okay, Same thing for the edge here, or edge loop here. Double click on the horizontal edge loop, central horizontal edge loop, Control Shift double click, bevel, offset mode proportional. Ew, why does it do that? I don't understand. 1 second, tab. That looks fine. Or is it? No, that's fine. Oh, damn, that's so annoying. Okay, fine. Do we do bevel? Give me a second. Slide. Slide is fine. Offset mode. Slide works. Okay, bevel seems to be not cooperating that well. Let me try one more time. Proportional straightness, keep creases, straightness 1. What if we do that? Ew, bad. 0. Okay, we skip the bevel. Instead, we will use slide. So you select the edge, you slide it, and let's slide it to the top. Offset mode proportional. And we just slide it almost to the, you know, as close as you can get to the side. Why can't I slide it closer? Hello? There we go. Yeah, actually, that's pretty good. Okay. So we slide it there. And you can see that the closer you get to the edge, the better it holds the shape, right? Because two edges hold the shape much better than one, right? It's just the same way as how many control points you have in a NURBS curve to, you know, to make a corner. That's exactly the same logic. And then I will just double click on that edge loop that we just used to slide, and I'll type in insert edge, offset mode proportional, don't forget, and I just slide it over to the bottom. There we go. Yeah, okay, that's getting there, you know. Still soft, but much better. Okay. Now, on to actually, you know, making some sort of a design. And I don't have that much time to make a design because I also want to do a triangle. So I'll just do something real quick. And you don't need to follow along with this at all. I'll just insert edge from the side to the middle here. Perhaps bevel it. Let's try to... Let's select both of the middle ones here, the top middle polygon that we have and bottom middle polygon that we have. Inset edge, not edge, sorry, just inset. It's like a offset only inwards. Enter, mode, single, enter, 0.1, that sounds good. That's good. You can also bridge between two elements, which I probably will do. I'm contemplating if I should. I will. Bridge. Now we made a hole in it. Looks very, you know, it is what it is. Then I will select these two, inset them again. Bridge between them. Actually, this might be 3 segments. Can I just kind of do something like that? Extrude it downwards to 0. Scale to 0 to flatten it out. And then last one, let's keep doing the inset, why not? Bridge, tab. Seems good, except for that particular area. This is smoothing out way too much. Trying to understand which part of it is smoothing out. think it's gonna be here, right? There's nothing we can do. Actually, I will let it crease because it seems like it's not self-intersecting, it's just creasing or bending over itself very hard, but it is not intersecting. I will just use a clipping plane real quick to check if I'm not teaching you any no-nos. Nah, looks good to me. Controlling the curvature of a shape is, yeah, that's fine. Controlling the curvature of a shape is pretty hard, generally speaking. I will sharpen the outside here by introducing a bevel. Not bevel, yes, bevel. By introducing a bevel up to a midpoint. Actually, we probably need 2 bevels, okay. For both the outside and the inside, and that's going to be the end of this particular element. And the second one, the element number 1 that I'll do, I'll rush through it quickly, quicker than this one. Let's do 0.05, something like that, just a very slight bevel, so that the tube here is a little bit more, pronounced compared to the tube here. Sub D is fun until things don't smooth out the way you want them to smooth out, and then sub D is hell. That's at least what I learned. Bevel 0.05. Is that straight? Yeah, that's straight. Okay. If I were to show you the guide again, the only rule is that this part, yoink, oh, too much. Give me. Okay, this part cannot do this. It should not ever extend beyond the edges of the voxel, never, right? It should always stay in here. That's the whatchamacallit, the rule. Yeah, that's the rule. Besides that, we're good to go. In terms of modeling out anything we want, you can do quick one, boop. You can do something like this, and that's fine. As long as you're in the voxel, no other element will use this space except for this element. Okay. Now I will repeat this, except that I'll be faster. So yeah, give me a second. 1, 2, 3. This moves 0.5. The gap between the elements, and by faster I mean I'll start making mistakes. 0.5 minus 0.5. The gap or the thickness of the elements needs to be consistent. If the thickness of the elements is not consistent, that means it's going to, the elements will not align properly, and you want them to align. Okay, finally. So we have that. Then I can just hide the guide, 3D face, first one, second one, bridge. Ew, too many. Bridge. Segments 1, okay. Okay. And last one here. Okay. Then for this, I'll do a little bit of a different approach. I will inset here, 0.1 seems fine. That kind of sharpens the edges, but it does not sharpen the edges right here. And then for that, I need to bevel these, the corners, I mean. I need to bevel these. 0.05. That's too much. That's going to be 0.005. Very small bevel, but that, you know, creates a pretty nice triangle. And then just a quick you know, design for it. Inset 1. Do we just extrude? I'm just gonna make a hole for it real quick. Bridge. Okay, that's good enough. Design hole. Okay, so we have two elements that we have just designed. Cell PT, delete. Boop. Guide curves. Okay. Now let me let's continue. Let's continue with this. I want to show you one thing that I find to be quite exciting. So we have made this script that places blocks for us, right? Or we didn't make the script, but we were using the script that places blocks for us, and we have certain whatchamacallit, certain point cloud that, you know, is ingested, and it uses the element names to place them, right? And let me actually disconnect the thing that I did during the break, like so, and actually just use the points, raw points, so to say, to showcase the workflow. Change object layers, and I will just copy 10 here, 10 here, 10 here. Sure, let's do like that. Something like this should make a okay form. Set multiple points, reset, no, calculates it, place block, places it. We have a form, we have something, right? Now, let me show you a cool thing, a quick one. If I select element 1, the one that we have just created, right? Or rather, I probably should, we don't need Grasshopper for this. I probably should split the screen, or not, the viewport into 2, so that you can see the elements here that are already placed here. So if I select element 1 that we have just made, and I type in block, it asks me for block base point, which is 0. I pressed it way too fast. Block base point, that is 0. And then it asks us for a name, and I type in EL1, caps lock EL1, hit OK. Would you like to replace it? Yes. All of the elements that we have here get automatically replaced by element 1. You get that for free. You get the updating. This is, by the way, not Grasshopper. This is Rhino updating the block definitions for you for free. Same thing with element 2. Block. Base point 0. EL2. Hit OK. Do you want to replace it? Yes, I do. Voila. All of the element 2s are now replaced for us. Sweet. So this makes it so that designing the elements and actually checking how does the design influence the overall structure does not even require you to redo the simulation in Grasshopper or anything like that. As long as the blocks are already placed in Rhino, they will update in real time when you change up the geometry for those particular block definitions. I find that to be very useful and very seamless. Sorry, give me a second, just thinking if we should move on. So now you're able to create the elements. you're able to manipulate the elements, you're able to replace the standard elements with your own creation, and you're able to change the form by changing the the points in two different ways. Okay, I think it is time to move on to Unreal Engine. Yay. All right, let's go to our folder. And here we're going to go to Tower, Unreal Engine 5.3.2, and just open up the Unreal Engine project. Just double click on it, it's gonna open up. And it's gonna take a while, of course, first time opening up any project takes a while, so I'll give you some time for it to load in. While it's loading in, please open up a new instance of Rhino and a new instance of Grasshopper. And in it, load in CMC to Unreal Engine 5 CMC to Unreal Engine Rhino file, 5 CMC to Unreal Engine, Grasshopper file. Load in these two. So in total, what you should have open at this point in time is 4 CMC for Students Rhino file, 4 CMC for Students Grasshopper file, 5 CMC to Unreal Engine Rhino file, 5 CMC to Unreal Engine Grasshopper file. Side note, when you will load in the Grasshopper file, it immediately will begin calculating. You can stop the calculation by navigating to Loop Start, right-clicking on it, and choosing Enabled to, clicking on Enabled so that it gets disabled. Right? You don't need it to calculate just yet. And then we wait. We wait for Unreal Engine to load in. I will ask at least one person in the call, once your once your Unreal Engine 5 file loads in, please let me know so that I can start a counter of a few minutes for the rest, right? So at least I need at least one person, once your Unreal Engine 5 file loads in, to let me know so that I know how far along are you with loading in the group, I mean. While that is happening, I will quickly, is my webcam starting to lag? Anyway, yeah, that's what Unreal Engine gets you. I'll quickly explain the Unreal Engine 5 project that you're looking at. Remember the 13 megabyte file? The 13 megabyte Grasshopper file, or sorry, Rhino file with a lot of elements that we had? Same shenanigans are happening with this Unreal Engine 5 project as well as the game itself. If I were to check the size of the game, that is 450 megabytes. A 450 megabyte Unreal Engine 5 game, right? If I were to check the tower itself, it's 600 megabytes in size. The reason why, just to be clear, usually when I do architecture visualization work and so on, we're talking 15, 20 gigabytes per Unreal Engine 5 project. So seeing 600 megabytes for a full game ready file or project file, that's small. And now I guess it's the time for me to show you the scale, the actual scale of it, while you're still loading. No one is telling me that Unreal Engine 5 loaded in yet. That's scary. Let me guess, shaders are being built. 60%, okay, yeah. Let me quickly switch to here. I just want to show you, that block that we have here. This is the level 2 block that I was talking about, right? The one that requires 8 hours to actually climb on top, actually complete, right? And that contains 7,860 points that are all wrapped around by, a bunch of meshes. I have another one, another point cloud. I wonder if I have it here. Give me a second. Yes, I do. This one. This one is fun. Let me hide that for a second. So this point cloud is grown, and it was grown. I had a separate script that is not part of this webinar, and neither should it be, because that would require a separate webinar in itself. I had a script that basically grows these points according to the shading values that these points provide for the previous generations of the system, meaning that we would constantly be doing solar analysis on every generation of growth, and the points that shade too much of the previous generations, that cast too much of a shade, would be eliminated, right? And we ended up getting this kind of a tower, which kind of makes sense, every time the growth shades too much, it gets cut, and then small branches start growing outwards again, right? So we ended up getting this tower. I have no idea what happened in this area though. I think that's just the... Oh, I know what happened. I remember. In this area, notice how the density of the growth just gets cut to pieces. I changed the values of tolerated shading. So here I made it much, much more aggressive in terms of how much shading can a structure cast, right? So the density just plummets, and we end up having just a single tunnel, and then I let it shade more, or rather I maybe even turn it off completely, and then it just grows, into infinity, and then I stop it, right? So we have this tower that is, grown according to light. How many points? 21,000. Did I catch them all? 23,201 points in total. Let me show you, I think. Level 1 of the game, Unreal is fully loaded. Okay, that's good. Level 1 of full game is that structure. This is the structure that you spawn in when you are playing the game, when you begin the game, and the end of it is the 100% once you reach it. So you can clearly see that, this is a bottleneck where, there are a few areas where, well, there's one area here that's kind of a dead end, but you can kind of re-bridge your path here. But the main bottleneck is when the shading values have been ramped up, or rather checking for the shading values have been ramped up. That makes a bottleneck where the players have to go this route to finish the game, and that destroys a lot of runs, which was fun, architecture plus video game design, yay. Anyway, more importantly, this is running at 120. Okay, this is unshaded. Let me shade this, and let me exponential height fog, turn that one off. Post-process volume, turn that one off. Okay, now you can see the full structure, right? And we are at, for me, 120 frames per second. And if I zoom into any one of these, that is not a low resolution model at all. You know, it has a 4K texture. Each of these elements has a 4K texture. And if I were to show you the wireframe of it, you know, there's quite a few polygons. The reason why it's not crashing the computer is because as I zoom in and zoom out, you can see, or actually maybe better with nanite visualization overview. That's gonna be too little on your screen. Let's go to triangles. Nanite visualization, you can see that as I go in here, there's a certain count or certain size of the triangles. As I move out, the triangles are being redrawn, right? The polygons are being redrawn according to the size of my screen. And it always just works. The limiting factor becomes not the size of the city that you create or not the size of the structure that you create, but rather the size of the Excel file that is used to load in the city, which I find to be extremely hilarious. Right, so that's our mega city. You can waddle around in it. You can actually press play, you know, and actually try climbing up and so on. This one does not have the awkward bunny rabbit character that I had in the video game. That one is just for me to check out the avatars and then how those can be implemented in a, you know, in an environment such as this. But generally speaking, like there are certain things that were changed for the character that you see here for the Unreal Engine 5 character. Main one being the climb speed and the position of the bones as the character is climbing a slope that is 45 degrees high, right? You don't want the character to be able to run up the slope. I always end up having here that going here. Maybe that's some sort of psychological thing. I don't know. Leaning right, I guess. That's a loaded one. Anyway, escape out of that. So let's talk about how do you get your elements into Unreal Engine, right? What's the procedure, I guess. The first thing to understand is, first of all, CMC to Unreal Engine 5, the logic and the way this whole thing works is exactly the same, right? It's we're using exactly the same principle. The only difference is that here we have an extra script. And from what I remember, sorry, let me just quickly read through the script. It's a lot of information. So some things that I was preparing for this webinar, I skipped over with hopes that, oh, I'll just see it and I'll just remember, but I don't. So there's two negatives. Why are there two? There should be one. That is -1. That joins up the text. Those are rotation values in Z, so it needs to rotate negatively in Z. Okay, understand. So Unreal Engine 5 and Rhino uses two different coordinate systems. That's a very important notion to understand before moving forward with any kind of importing or manual importing from Rhino into Unreal Engine 5. And what I mean by different coordinate systems is left hand coordinate system. One uses the left-hand Cartesian coordinates, while the other one uses the right-hand Cartesian coordinates. And I guess this image is a little bit crappy. Let me find a better one where both of the diagrams have Z pointing upwards. Hello, Z upwards. Any one of these, please? I hate my life. Okay, yeah, perfect. That we use this. Nice. Z pointing upwards. Y is to the right. X is to the left, or X is towards us. Z pointing upwards. X is to the right. Y is pointing towards us. Take a look at this. If I look at Rhino here, bottom left hand side corner. If I look in Rhino, Z is up, Y is to the left, and Y is to the right, and X is pointing at us, right? If I look in Unreal Engine 5, Z is up, X is pointing to the right, and Y is pointing at us. X and Y are flipped. They're not really flipped, they're just, yeah, it's a different coordinate, left-hand side versus right-hand side coordinate system. This cost me around 4 months. I thought I was going mad. I thought that I was crazy. Everything that I import gets flipped, gets mirrored, does not rotate correctly, and like all of the axes are just everything is kind of there and almost fine, but it looks like it's either a mirrored version or it does not follow, like only in one direction. In Z axis, everything is fine, like everything grows, but in other axes, everything is misaligned for 4 months until I figured out that, yeah, it's just different coordinate systems and you just need to convert to them. Because of that, as we are converting the, I'll talk about the Excel spreadsheet in just a second, but as we are converting all of the data from Rhino into Unreal Engine, we need our Y location to go in the negative, so it goes backwards, and we want our rotations to be flipped. So the rotations need to, around Z in particular, to be rotating backwards. As long as we have these two negatives, it works. Yep. So that was painful, and you know, I just wanted to explain it to you and showcase it to you. Okay. Now, before we move on, let me do a quick. I'm just scared of pressing the data down. Before we move on, let me do a quick explanation of what is it that we do and how is it that we transform or translate the forms from Rhino and Grasshopper into Unreal Engine. So easiest way would be to, you grow the tower out of the blocks and you export the tower, you import it as FBX in Unreal Engine 5, you load it in and you're good to go, right? You're ready. And I'll have this as an unlit mode because lit mode is just destroying my computer's performance. That doesn't work and that breaks completely. The moment you reach a few billion polygons, the FBX file becomes unstable and impossible to export, import, and so on. So you need to deal with those 13 elements. And for this, first of all, I will show you the elements that this particular Unreal Engine 5 project has. First of all, let's go to our content drawer here in the bottom left. Go to the My Stuff folder, expand that, and go to Elements. These are all of the elements that are used, right? All 14 of them. That's the only geometry that is imported into Unreal Engine. Then let's go to top right corner, outliner, and let's just check out of what we actually have in this level. Not a lot. We have our fog, the floor, which is literally just a plane. It's just a rectangle, right? The floor is just a rectangle. We have instance foliage actor that I have no idea what that is. Oh, I remember. I checked out if I can grow trees in the structure. This does literally nothing. Sorry, that's a whoopsie. We have a player start. That's where our player character starts. We have sky atmosphere, skylight, volumetric cloud. All of these are just for the light and then for the atmosphere. And then we have our element BP, element blueprint. And as I select it, my whole damn structure gets selected. And I can move the structure, right? By just selecting the blueprint and by just moving the blueprint. That means that there's a single blueprint that is responsible for constructing this whole thing. Okay, so we have one blueprint and we have 14 elements that are used to construct that blueprint, or that blueprint uses to construct the tower. Great. Let's look at the tower, or let's look at the blueprint rather. I believe it's that's just on My Stuff. We have element BP. Double click on it. Opens up a new window. I assume you have at least a beginner level knowledge of the blueprint system in Unreal Engine. It's basically like scripting in Grasshopper versus programming, same thing in Unreal Engine, C++ versus the blueprint system. So blueprints are, as you can clearly see from this, the Grasshopper file for Unreal Engine. If I go to viewport, you can see our tower here, great, the viewport tab. And then on the left-hand side, I have all of my imported layers. Elements, sorry. If I select element 07 or 06, you can see all of the elements that are used that are 06, 05, a lot of element type 5s are used, 4, 3, 2, 1, 14, and so on, right? One is used mostly on the corners. Okay, cool. So there's something happening. There's something that's placing them. If we go to the event graph, well, that's empty. And the reason why event graph is empty is because once you press the play button, once you start the game, nothing happens with the structure. The structure does not change. So no events happen. But what happens is before you press play, the construction script actually constructs the blueprint, right? So construction script is something that happens before the game even starts. Okay, guiding you through this will be, again, I'm doing it backwards, right? I should show you the Grasshopper script and then show you the Unreal Engine, how that handles it, but I feel like doing it backwards makes a little bit more sense because then you know what to search for in the Grasshopper script. Let me go get you through this chain of events. You have the construction script right here. You have the data table row names. That means there's a data table somewhere. Data table, think Excel spreadsheet, right? Let me show you the data table. If we go to the content drawer in the bottom left, CMC to Unreal Engine Excel data table, right? Double click on it. there are rows, there are columns, and for every row, horizontal line, you have columns that are talking about the element index. Element index is the type of the element that talks about the location, x, y, z location, and rotation, rot x, rot y, rot z, right? So basically what this does, it takes every element, or every voxel, I guess, and it says what kind of element it should use. So element index 0 is the first element. Element index 1 is the second element. It's weird because you start counting from 0, but it is what it is, right? So for instance, let's look at row number 1, right? Expand that. For the first element that is going to take will be element type 1 because it's element index 0. Its location is going to be minus 1000, 1000, minus 1000. That's the coordinates. And its rotation is going to be 0 around the x-axis, 180 around y-axis, and minus 90 around z-axis, right? So it basically takes the first element, moves it in place, rotates it in place. It takes the second element, which is also element type 1, moves it in place, rotates it in place, and so on. And it just goes through this whole damn thing. 31,391 elements in total. We go back to the blueprint and we look at how does this work. Okay, I need to drink a little bit to explain this one. It's water. Okay, we have ourselves a construction script. We have this basically just triggers every time. It's just a trigger that runs the chain of commands, right? We have the get data table row names. So the first thing that it does, it reads the table and it gets the names for each row, not the column, doesn't care about the columns, it cares about the rows. So row 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, 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 right? So these are the row names, they are just numbers. Gets the names, and then for each row name, so for each row, it will extract the information of that row, right? So it just goes through every row one by one, and it just extracts the information. Then we break out the information that we got into its components, and that's where we get the element index of the first row, the x location of the first row, y location, z location, rotation x, y, z. Great. We have all of the information for every row, right? And it just kind of loops through, through every single one of them. Okay, for the first row, our element index is 0, right? So it's going to spit out 0 here. And what do we do? From all of these elements that we have here imported, you know, these are our imported FBX files. And I'll show you how to do that in just a second. But these are our imported FBX files of different types of elements. You can see here, if I select 04, that's the static mesh is element 04. If I navigate to it, double click on it, that's my element, right? And I just create an array, a list, if you will, you know, of these elements. And then by a sheer index, you know, as it's going, I'm just picking an element from this list that I have created. So 0 comes in here from this list, it fetches element type 1, right? So now here we have element type 1. And then all I need to do is for that element type 1 is I add it as an instance. You know, instance is the fastest way of how you can display a mesh. It's limited to a certain degree in terms of what you can do with it. You can't run certain simulations on it, but for environment, that's perfect because it needs to be static. That's all it needs to do, right? So we add instance. It requires us to things for it to work. First one is the target, which is basically what's the element that you're adding. So we're adding element 1 for the first row, right, of our Excel spreadsheet. We're adding element 1, and then it asks us for what's the transform, how is it located, rotated, scaled. We make a transform and we get the same information, X location, Y location, X, Y, Z locations. We make a vector, we add it to a location, rotation X, Y, Z. We make a rotator. For some reason, they don't use a vector for rotation. They use a rotator. By they, I mean Epic Games, Unreal Engine makers. We make it into a rotator. And for scale, we don't mess with the scale. We keep the scale as it is, 1, 1, 1. We have this done. And then it just makes it, right? It goes through every row because of the for each loop that we have here. It goes through every single row that we have here and just keeps placing, chooses an element, location, rotation, chooses an element, location, rotation, and just places it according to the instructions, a key assembly manual into the tower that we have. Hope that this makes sense. So the only thing that we really need to do on the Grasshopper side of things is we need to explain, or not explain, but construct this Excel spreadsheet, right? And that's very easy to do. Let's do, should I improvise? If it works, it's gonna be pretty fun. I think we should YOLO. Yeah, let's improvise, why not? Okay, so I assume you still have CMC for Students opened up, as well as CMC 2 Unreal Engine opened up. Right, do we improvise? Here we only have 2. Okay, let's have a 5 less. Now it's 2. Let's have a 3-minute break. So toilet and so on. 3 minutes, 55 past. We meet up again and then continue. In 3 minutes, I'll decide if we improvise or if we stay on script. Okay, 55 passed. Let's continue. So I have decided to jazz it up just a little bit, not 100% jazzing it up, but like 70 or 50%. We will be connecting the two scripts, not scripts, sorry, the two files together. So the first part that I want to do is we don't need to see this tower. So points for CMC in the CMC to Unreal Engine 5, to Unreal Engine Rhino file. We just hide that layer, don't need it. Second thing that we do in the same CMC to Unreal Engine Grasshopper script is we disconnect at the start of the script on the left hand side, we disconnect random reduce from the point input. We will use custom points for this test. Bam. Delete. I just deleted the left hand side, so we will not be using that. So this is waiting for us to give it a set of points to work with. And let us actually create a few points. So I'm just going to create one point at 0, 0, 0. ZS to zoom in. Actually, I want to check one thing. Just give me a second, because I think, yeah, we're using 1,000 centimeters. Okay, that's going to be one more thing that we'll need to change, but sorry. A single point at 0, 0, 0, and then one more, or two more. But now this CMC to Unreal Engine file uses voxel size of 1,000. You can check, by measuring the distance here of these voxels, or by simply looking at this slider here, 1,000, meaning it's 10 meters sized voxels. Makes sense when you're creating an environment to walk in. So here, as I'm going to be copying this point, I will be copying it not by 10 but by 1,000. 1,000 and 1,000 here, and maybe like that. Yeah, 4 points, why not? Don't forget to always go into the positive X and Y as you are copying the points. Set multiple. Activate or loop start. Make sure that it's enabled. Press the reset button. Click the button to place block. Great, it places the blocks, right? Oh yeah, and this is how it looks like with the blocks that I have made. Again, these crash a lot. So now we want to, now we want these points to appear, not the points, but this structure that we have here, we want it to appear in our Unreal Engine 5 environment, in the environment that we have for Unreal Engine 5, right? So that is where the Excel spreadsheet comes in. If we navigate to the top here, you can see all of these data dams on the left-hand side. So I will just click on each of these data dams to let the information through. And I'll explain what each of these are, right? So click, 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 3 data dams, the orange group. First one, or actually here I have even named them. First one is transform, second one is name, third one is voxel position. And if I just kind of move them properly to the corresponding ones, you can see that the name gets sent through the top data dam and it gets sent as text. I can show you what kind of stuff goes through here. Apologies. Element names, EL1, EL2, EL4, blah, blah, blah. Then I go through these, each of these names, and I split them into separate characters. EL1. I remove index 0 and index 1 of this list. So I'm removing E and L, and I'm only keeping the element number in. And for the numbers that are, okay, it's not using any elements like 10, 11, or 12, but if it did, then we join them up. And then I subtract 1 from them because element 1 needs to become index 0. Element 2 needs to become index 1, right? So I'm subtracting 1 to them. I'm giving the column a name, EL index, and I'm merging it with the list that I have for subtraction. And basically here I have EL index 00130001 and so on, right? And basically that is in Unreal Engine, that's what I have here, EL index. Shouldn't have done that. 1 second. There we go. EL index 000010141114 and so on, right? We have constructed the first column. That is here, the element index column. Okay, next. Well, technically the first column is the index itself of the data, of the row names, which is literally just a counter for how many elements we have, but that's whatever. Second one is getting the voxel positions, which is very easy. The information that arrives is XYZ positions of the voxels, you know, for the basically elements to be placed in. I separate them into characters. I remove the first and the last character of each list. I can show you why. Because it's the brackets, right? I remove the first bracket and the last bracket of the list. I join them up again. Now we have a list like this. I split the list according to a comma. So now I have 3 values here. I convert them into numbers. When you convert text into numbers, it removes all of the spaces, right? So I do that. And then I separate them out, you know, into X location, Y location, Z location. So we have 3 more columns that we have created here. And I guess I can show you. I split the compound transforms here. So rotation about X-axis. We split with a space bar, right? So we have rotate degrees about X. I get the degrees. I separate out the degrees. Remove the, why is it -1 and -2? 1 second. Oh yeah, because it's the degree character here that I remove from here. I join everything up. Now we have the degrees. And you can see, let me show you here. Why the hell is that? That's weird. That one is strange. That shouldn't be like that. Why is the last compound transformed this? Because it's a move. Okay. Typical. Yeah, that's a typical webinar behavior right there. Suddenly we have a move compound transform. That's fine. For now, I will let it slide and I will just see what kind of a structure are we getting here. Oh, the move gets removed for some reason. 1 second. Oh, I'm very confused. Give me a second. Join it, trim it, split it. from zeros. Oh, the move compound becomes degrees, or rather becomes reshuffled into zeros. I will need to take a look at this, but I'll take a look at this during the next break that we will have. Apologies for this one. That seems like a bug on my end. Something with the script. Curious. Anyway, for now, let me just double check. The placement seems to be working fine and everything is under control. Okay, that's fine. I will take a look at it during the next break. But basically, we then just merge all of the columns together into one big happy list. We join up the text with commas, right? So I can show you how it looks like that, right? So everything is separated by commas. And then we generate this. Don't forget to press the data dam play button. We generate this list, right? Or not list, but a document. Important part. You right-click the document, the panel. You choose to stream. You choose stream destination, and you just go to desktop, wherever you have downloaded your Design Morphine folder. Stream to that folder and just name it testing Excel. That doesn't matter. Name it whatever you want. And make sure that you choose CSV, comma, separated value files. CSV is an Excel spreadsheet type of a file, but the way it's described in the Excel spreadsheet is by comma separation for each column. That's why we do it the way we do it. That's how we encode it, right? CSV. Hit save, right click, make sure that stream contents is highlighted, I guess, that the little save button next to stream contents has the blue outline. That means every time you press this data dam, that CSV file that you have saved will be overwritten with a new version without you needing to do anything else, right? So it's gonna be streaming constantly. Okay, with that done, we go in here into our Unreal Engine file. My stuff folder. And here I will be importing the CSV file that I can't find. What? Didn't it got written? Hello? Am I blind? Okay, I'll do it again. Right click, or maybe I need to stream contents, like toggle it twice for it to actually register. Yes. So if you can't see your CSV file, just make sure to right click stream contents once, right click stream contents twice, then it's going to kind of trigger the first save. All right. Let me open it up for you to show. That's what we're importing, right? Positions, element types, positions, and locations. Really hope that this is gonna work, or else I'll need to troubleshoot or debug a few things. Anyway, going back in here, let's actually make a few copies. So if you're lost in the mega structure that we have, just navigate to player start or select player start and press F key, F to focus key. That's going to immediately focus on the player start icon. That's where the game starts, right? Great. Let us, in our content drawer, element BP, let's just right click on it and choose duplicate. That's the first thing that we're gonna do, duplicate. And let's just call it testing. testing structure or whatever. Testing structure. We're going to be playing with this one, right? One important thing before we import the Excel spreadsheet that I want to address is that the Unreal Engine in itself will not understand would not, if this was a completely empty file, it would not understand how to read the Excel spreadsheet, right? What it needs to be able to read the data table or the Excel spreadsheet is a structure, right? And you can create a struct by right-clicking. Don't do this, by the way. I'm just going to showcase how you would do it because we already have a structure here. You would right-click. You would go to, give me a second, input, I guess. No. Yet again, yeah, there we go, blueprint structure, right? You would make the structure, you would call it any way you want, double click on it, and here you would start saying, well, it's going to have, the first row that is going to have will be EL underscore index, EL underscore index, and it's going to be an integer, a full number. Then I press the add variable key. Next one will be X location, X lock, X underscore. It needs to match up, by the way, very important. X underscore lock, and that is going to be a float because it can go into the negatives, and also if you're dealing with like voxels that are less than a full number, then it needs to be a float, and so on. You keep adding variables. I'll show you the finalized struct that I use for this file. Delete this one. Double click. See? EL index, X lock, Y lock, Z lock, rot X, rot Y, rot Z. Now Unreal Engine will, with using that struct, will understand how to interpret the Excel spreadsheet. Let's drag and drop it in to our My Stuff folder in Unreal Engine. So testing Excel.csv, drag and drop in data table. Yes, it is a data table. And then choose data table row type. That is going to be our CMC2 UE struct. That's the one that I have created. Right? Apply. Yay, we have our testing.excel or testing.excel.csv imported here, all ready to go. Now, let's work with that blueprint, right? Testing structure blueprint class. Double click on it. And all you need to do is just go to the construction script right here, zoom in, where it says, so testing structure, construction script, where it says get the data table role names, you just choose the spreadsheet or the data table that you have just imported, which is going to be called testing Excel. Then we go to get data table row, expand that, also testing Excel. There's only these two places where you need to change things. If I go to viewport and I click on compile, now it just gives me the, why does this work? It should not work. Well, it does work because movement gets overwritten by 0, 0, 0, meaning that probably if the rotation is 0, if there's no rotation, then movement is used. And then since movement is used, it's just defaults to 0. So it's just a happy accident that the bug eliminates itself. Huh. I will not address that. It just works. Don't worry about it. There was no move instead of rotate bugs. So now we have this small struct that is, that is driving our shape. I can save it. I can go back to my level, go to content drawer, testing structure, drag and drop it in. Voila. You have a structure inside of the mega structure. Let's play. Why is this so freaking? Oh, I know. If that happens, that usually means that, let's F to focus. If that happens, that means that our player start is trying to spawn inside of the structure. So I'll just move it to the side a bit, play. There we go. And there's our new thing that we have made in Grasshopper and imported in Unreal. That intersects with our, whatever. Hopefully that makes sense, right? Let me show you how you export an element, your own element, and replace all of these elements with your element. Back in our CMC for students file, we have made this triangle. Do we do a triangle or do we do, let's do a triangle. I'll just replace this one. Okay, there's a few moments to this. First one is the scale, right? So what I will do is I will create a box. Actually, I will first, apologies. Let's go to the shaded view. It's annoying without it. I will select my element, my block, and I'll explode it. When you explode the block definition, it reverts back to what the element was before it, but it retains, if I go to block manager, you will see that my element one is still the same sub-D object, right? So it remembers that the block stays, except that this geometry right here is not a block anymore, it's a sub-D, right? So that's the first thing. Okay, let me create a box right here. This box, and as well as this element. I have these two. I will Control C. Do we need to do that? I probably should do it in a clean way, just to show you. Okay, I'll show you in the way of how I do it, which is a little bit longer, but it gives you the most amount of control possible, and it's the cleanest. Open up a new Rhino file, completely new. Type in units in the command line, units, and change to centimeters. Okay. Create a new layer, call it EL1. That's where your element 1 will live, EL1. And then the element that you have here, together with the box, Control C, copy, and Control V, paste into this new file that you have created. This is going to be our exporter file. Okay. Now I want this element, or this box rather, to be 1,000 centimeters in its sides, in its, how big it is, 1,000 centimeters. So I scale from the bottom left to the bottom right, and I just type in 1,000, right? Okay. position of the box in the world matters during export, unless you're using export with origin, but it's better to just position the element with the box properly. So I will just move the bottom left corner of the box to 0, 0, 0, and then just move it so that the middle of the box is on 0, 0, 0. So minus 500 in X, minus 500 in Y, minus 500 in Z. The box is now rotated around, not rotated, sorry. The box is now locked around 0, 0, 0. Very important. The reason why it's so important is because the element that is going to be exported will be rotated around the 0, 0, 0 point during the, the rotation, and you want it to be, always snapping to the size of the box. That's the reason. I will select the box. I'll type in silhouette, and I'll create a new layer, call it cage. Right click, change object layer, lock the cage layer, delete the box. Now I have curves in the cage layer that show me the bounds of the voxel. Always nice to have, right? Almost there, almost there. Now we open up Grasshopper. Typical. We need to replace this object with a mesh, because that is what we're going to be exporting. We're not going to be exporting a sub-D object, we're going to be exporting a mesh. Very easy to do. One of the reasons why we installed, did we install ViewerBird? I hope we did. If you don't have ViewerBird, I will show you very quickly how to install it. We will need ViewerBird plugin for this. If you go to Rhino, command line, package manager, and here you type in ViewerBird, W-E-A-V-E-R, ViewerBird. Select it, click install. We'll ask you to restart Rhino, so please do. Once you have restarted Rhino, you will have that plugin available for you in Grasshopper. So let's assume that you are needing to restart Rhino. I will file, save as. I guess that's going to be still 5 CMC exporter. Save. Don't forget to save your Revit file. This is not your Rhino files. Close. CMC exporter. Open it again. Now you should have ViewerBird in it. Please don't open with Rhino 8 suddenly. Oh, come on. Give me a second. I don't know why Rhino 8 really wants to open all of my files. But no, we still use Rhino 7. Most of the people still use Rhino 7. Okay, like that. Open the file. Great. Position the things here. There we go. Hello, where's my layers at? Oh my god. Everything that can go bad goes bad, right? Layers. Hello? Layers? There we go. Just place them here. Okay, Grasshopper. Sub-D needs to be converted into a mesh and then subdivided. ViewerBird will deal with subdivision. We reference in sub-D. Set 1. Pop. What do? We extract cage. Mesh cage. Okay, fine. I will use the old-fashioned way. We go to the mesh tab, sorry, we go to the surface tab, we go to the sub-D tab, and we choose, you can either do mesh from sub-D, that this would work, or you do sub-D control polygon and then use Catmull-Clark subdivision. Weber's Catmull-Clark subdivision. Either like this with level 2 or like this with level 2. The reason why I tend to use Catmull-Clark, let me hide that. Level 2 is a little bit poor. Let's do level 3. The reason why I tend to use Catmull-Clark subdivision versus sub-D subdivision or sub-D conversion is because it used to, like this node used to give me errors and make mistakes. But it seems like now it's fixed, so we can use this one instead if you want to. Either way, we just bake into element 1 layer. Okay, now we can delete the sub-D. And that's it. Now we have ourselves element 1, right? Right here. Very simple script, very, easy. Sub-D, mesh from sub-D, or sub-D cage, Catmull-Clark. If you are doing a print screen thing, then I'll show you this way so that you know what's what. Okay, once you've done that, then it's time to export the element. I will just select it, export, choose to export it. Because it's positioned correctly, now I don't need to deal with anything else. I'll create a new folder, call it elements or L export, I guess. And here I'll just call it element 1 design morphine DM. And I'll just choose motion builder FBX format. Clearly, I see it. Yeah, there we go. Motion builder FBX. Hit save. Oh, I should probably show you the options that I use. These are the options that I use. Map Rhino Z to FBXY is one of them. Besides that, I believe I use everything else is just default. Okay, we have the FBX file now, exported, back in Unreal, content drawer, elements. I'll create a new folder, call it DM elements, right? And I'll navigate to it, EL export, FBX, drag and drop into your content browser window. Gives you all of these settings here. The only one that you need to tick mark is build nanite. Everything else should be default if I remember correctly. If I don't, then we will make a few adjustments. Import all. Element and its layer, element and its material have been imported. If I double click on it, seems to be okay. I'm still a little bit on the edge about it. Oh, by the way, this is also not part of the webinar, but I noticed that people tend to struggle with this. If you have ray traced shadows turned on, nanite will make shading issues, shading mistakes. This happens all the time. And the reason why it happens is because it shades against a fallback mesh rather than the actual mesh that is being displayed. And the way of how you can, to a certain degree, mitigate that is by choosing fallback target, not to be auto, but rather relative error. And fallback relative error, if you choose that to be 0. So it should not make any mistakes when calculating the fallback target. Then the shading gets to a certain degree fixed. I believe, you know, if I zoom out, you can see that sometimes it shits the bed and it starts making mistakes, but usually it's pretty decent. So ray traced shadows have been a problem for a long time. That's the fastest fix. There are other fixes that are a little bit longer, but that's the fastest one. Anyway, that's our element 1 DM. Let's see if we can replace it for our this lit environment that we have here for our smaller testing structure. If we can replace our my element that I have with this that we have made here. So I go back to my stuff. I open up my testing structure element here. I go to, on the left hand side, under components, I go to 0, 1, which are all of my element 1s. And here, all I need to do is replace the static mesh, as well as the material, because the material will just freak out. The material is custom made for element 1 that we have here. So I go to my DM elements, element 1, DM. Please don't break. There we go. Perfect. You can see that the material is not very happy with, actually, yeah, not the best. I mean, could be worse, but not the best. So I'll just make it white for now. You can just grab a material, just add it in, compile, save, look at it, just look at it. Everything is working perfectly. And now you can just iterate through designs like it's nothing. One thing that I also would like to note, if I were to undo this and just really quickly, these guys in set group 0.1, sure, gumball align to object, extrude here, you know, inset again, group 0.1. Oh, they're very small insets. Okay, never mind. But you know, I just made something. I made an adjustment, so to say, to it. Right click, set 1 sub-D, bake it in, hide the sub-D geometry, export the mesh again, and I just override this FBX file, right? Element 1 FBX, save, yes. All I need to do for this damn thing to react is go to content drawer, element 1 DM, right click on it, re-import. And it just changes, right? So this is a very quick, like the way you iterate through designs and the way you can evaluate the designs is very quick. You know, you can just do it very snappy, very fast. Is that the end? Well, at least that's part 1, right? There's 2 ways. This is what I have been working on for a while, and this is where I am currently at with this workflow. You can grow extremely large things with this. You can customize them at element scale. You can customize them at skin or silhouette, I guess, scale. It's a flexible system, and I hope that you will be able to play with it, you know, and find use cases for it. I think there's plenty, and I'm barely scratching the surface. In terms of the light, I just want to show you. I'll talk about the shade of the tower in just a second, but it's very much different from what we're doing here. But I will touch upon it during the next break that we will have. Let's do it this way, which is coming very soon. So one thing that students don't know about working with light is this really cool key command, or not key command in Unreal Engine, that is Control L and just holding the L key. Control and holding the L key and just moving your mouse around. You can control the light angle. Very nice, very useful. Can do a sunset. Very sacral. Okay. So that. Now we are finished with first phase, with first part. Let me sure. Save everything and we can start closing things. So just to kind of explain real quick, we use the Grasshopper script that we have in CMC2 Unreal Engine to generate an information of how the elements will be wrapped around any point cloud that we give it, and we generate an Excel spreadsheet with it. Don't forget the data dams, this one here and these three right here. Every time you change things, you need to press the data dams. They slow, like this part slows down things quite a bit, so you want the data dams there. So that's the first thing. Second thing is we have a separate exporter file that has a voxel right in the middle, so that you can just, get your element in there and mesh it, make it into a mesh, export it, check it in the structure. It's nice to have it as a separate file and Control-C, Control-V, copy-paste your elements in it, rather than having everything in one big file, simply because of the flexibility. Especially if you have two screens, this is much more controlled and you know what's going on and which version you're dealing with. I tend to have two main layers, one called sub-D, element 1, 2, 3, 4, 5, and other called mesh, element 1, 2, 3, 4, 5, so that I can always go back to sub-D and make adjustments to it. So that's that. Yes, I do want to save. I don't want to save the Grasshopper file. And the one that I showed you, CMC for students, that one was, just to show you the principles. Mainly you use the CMC to export and then the exporter itself. CMC to Unreal Engine, Rhino and Grasshopper file, as well as CMC exporter, Rhino file. No, we don't. To save anything, close. No, close. Okay. So that is that. Okay, let's have a quick break. How much time do we have left? Wait, we started. So it's now 3 hours, 40 minutes have passed. Am I correct about this? Or am I losing my mind? I believe it's 3 hours, 40 minutes have passed. Okay, so let's do a 10-minute break, something like that. And during which I will just prepare a little bit about the shading, the shading script. I might even try be able to find it and show it to you. Actually, 10 minutes, yeah. Let's do 10 minutes. If I need to, I'll expand it to 15 minutes. So now it's 40 past. Let's meet up 50 past. And then we'll talk about shading a bit before moving on. All right, let's continue. So a little bit of an intermission between the two modes of populating an Unreal Engine 5 environment with elements, with architectural elements, with architectural entities, the skylight analysis or sunlight analysis script. As you can see, it's a bulky one and it's a pretty heavy one. And currently I have troubles with resetting it or making it stable. I would need to take a look at, a little bit closer to all of the data dams and which one of these does not let the the data to be reset. It might be something here. No, I'm going to give up soon. But anyway, just to quickly explain how it works or how it should work. Probably I'll just disable it and I'll just show it step by step. First step is constructing or extracting a smaller portion of the mesh from the ground mesh from the larger site file. Second portion is populating these towers according to whatever outline we have drawn, right? So we have these grid-like towers, voxelized towers, I guess, of points, and then just checking if the points are inside inside of this brep, meaning this landscape brep, and if they are, just culling them out. And in doing so, just having the points, the points that are above the landscape only, that are left, right? And then from all of these points, all we care about is just the points that are the closest to the landscape, which is coincidentally, after we have culled away, those are the first points in each list, right? So we get all of them. Then what happens here is, let me enable this. We use honeybee, or is it ladybug? It's a script, okay. It's gonna be honeybee, not energy. Give me a second. Maybe like that. No, that's also a script, also leads us to a script. I hate that they do that. No, it's going to be Ladybug. Okay. So we use a Ladybug plugin for this to get a sun path in here and then to understand how does the sun move, right? And extract specific days and dates from the sun path, right? And what we are interested in are these vectors. So vectors from the position of the sun towards our each of these elements, right? So the vectors can be used to construct a shadow. When we do this, let me enable this part. We run a loop through each of these points. A loop is being run. We construct a voxel mesh, right, for each of these points. And what we do with it is we actually measure how much light does each surface of the voxel get, right? As it's being calculated. Let me reset this and then show it again, right? So all of these are getting a bunch of, like a decent amount of light, but now as the new ones are created, some of them are dropping to 7 hours per day. And 7 hours is still completely normal, right? So that's the direct sun hours thing. And what I say is if these surfaces for each voxel measure all of the surfaces that each voxel has, and if all of the light hours for all of the surfaces for each voxel end up being less than 3 hours, then you should you should not build it. You should kill it, right? And thus the loop is constructed, and we get, you know, the first batch of points is created, right? We make sure that our basement level also always does not shade itself too much, right? So that's our base level. Then we transfer it. We transfer it to our second loop, which will require, I guess we do this whole damn thing then. And then more so here. So much stuff. Okay, all of this. Basically what this loop does, and I am very confused as to why the hell is it growing upwards so much? It should do the next generation of growth. And just give me a second now. I'm going to double check why that is. What's this mesh? Oh, we're growing in a sphere. That's good to know. I didn't know that we're growing in a sphere. Sure. But basically here we have the previous generation of points, and for some reason the previous generation also counts these guys, which makes no sense. I'm sorry, give me a second. That needs to be reset. How does that look? That's bad. And there's a loop in here as well. Yeah, that's what happens when you stack loops inside of loops. You end up saving too much stuff. Okay, so then this needs to reset and this needs to reset. Not simultaneously though. Okay, this is where my explanation starts falling apart. I'm sorry. Okay, it seems like this will work. Okay. Enabled. Yeah, there we go. Okay, good. So now we're growing on top of the first floor. We're growing the second floor, and it's for every instance or for every element that is placed, it's checking the shading of the bottom floor as well as the current floor if the newly placed element is shading it or not. And then once this is done, you know, once the second floor is grown and it's yeah, current gen is empty, then we can actually yoink, go in here, press play here. You can actually visualize it, right, and showcase it. And then the next generation is grown, like generation 3, right? So we keep on growing on top of the existing shape for each generation, just checking the shading values of the previous generation. I think it's better to show it, you know, in the structure itself. This is like the colors are for each element placed. It checks the surrounding elements and just checks, you know, if the shading values are still poor or not and how poor they are. So you can clearly see that some elements or some values are already in the blue, in the blues, and the blues are 4 hours currently. So they are still being placed because it's larger than 3. If it reaches 3, 2, or 1 hour, the elements don't get born and don't get placed. And by the end of it, all we get is, you know, points for where elements should be created, right? So it's done in these steps, and it's a long script. I don't want to get too much into it. It's yeah, 10 minutes have passed, so that's a quick breakdown. It's done in generations. Next generation calculates the shading of the previous generations, and it just eliminates, plucks out the elements that are shading too much. Let's say it like that. I can upload this to. Wait, I'll just let's do it like that. New folder, shading, Grasshopper. Okay. It's gonna be available, so you can just go to the Google Drive and download the Rhino Grasshopper file, and there's gonna be a PNG there as well. You can just download them and try to make sense of it. Try to, play with it and see how it was built, how it works. You will need pufferfish as well as Ladybug plugins for it to run. All right, moving on. So now custom marching cubes script. CMC, by the way, is custom marching cubes. Marching cubes that are customized to fit with the design that you want, right? That's where CMC name comes from. My invention. Let's move on to a different approach. And this approach is much more built into Unreal Engine, and I think it's I have begun investigating it half a year ago, so it's I'm still pretty green on it, but I think I already have a little bit of insights for you to learn from and perhaps build up the knowledge base from what I show you. So the first thing that I will do is actually, yeah, let me open up Unreal Engine 5 project to showcase one, to showcase one thing for you, and that is going to be my playground, I believe, yes. Just a second. You will not have this Unreal Engine 5 project. That is fine, because that is not, it's not part of the webinar. But this is just for me to show you the system that we will be using, and basically to showcase what the system is typically used for and how we will kind of leverage it. That is not the playground that I want to show you. Let's go to maps and we go to landscape. We'll need to give it a little bit of time. Okay. So this is, perhaps I need to zoom out for you to see it. This is called a smocking form, right? When you have, maybe I can show you. Not smoking, smocking fabric behavior. It was simulated in Grasshopper, and I just wanted to see what kind of a landscape vibe, how would the landscape feel if you were to walk through this? I was very interested to see how, how would you experience a space standing in between this smoked fabric. So I have created this landscape, right? Or exported this landscape from Grasshopper, of course, into into Unreal Engine. And now if I play this level, give it a second, please don't crash. There we go. If I play this level, now I can actually, run around and experience this space. And you will notice that the elements that are placed here, the rocks and the fern trees and so fern leaves, sorry, plants, fern plants, they're placed according to certain rules. It's not like they're placed everywhere randomly, but the rocks are placed where we have a pretty steep slope, and the ferns are placed on, a little bit more even surface. And then as I go into, something that like this cave, it's, rocky, and it starts, it's not there yet in terms of realism and in terms of quality at all, but it starts getting there. And just considering the sheer amount of elements, that got me intrigued. Because these are megascans blocks, right? These are really heavy elements, and I have so many of them, a lot of them. So this got me intrigued, and this is why I'm now kind of moving forward with using this system to see if we can work with architecture and generally, architectural spaces, structures, and so on. The system is called PCG. It was introduced in Unreal Engine 5.1, I believe, or maybe 5.0, I don't remember. And its PCG stands for Procedurally Generated Procedural Content Generator. Yeah, that's what it stands for. Got myself confused there. And the way it works is also very Grasshopper-esque. It's a separate system from blueprints, just to be clear. But if I were to, click on this PCG graph and I open it up, again, you don't have this Unreal Engine file. I will just quickly go over it in like 10 more minutes and then we will move on. But if I look at this PCG graph right here, this whole chain drives the spawning of all of these elements, right? That's the logic. And I can really quickly break it down for you of how it works. Mesh sampler takes the landscape mesh. I can show you. Mesh sampler takes this mesh, that I have imported, and it populates it randomly with Poisson sampling. It just populates it with a bunch of points. And I can here choose under sampling options, what's the radius, how far away are points from one another. And I believe sampling radius is that there's no way that that's in centimeters. So that must be in meters, 0.8. Unless my mesh is scaled. Now I'm confusing myself again. I will stop confusing myself. Anyway, it populates random population of points on top of a mesh. Easy. Bounce modifier, self-pruning. These two just cleans up the points and makes sure that there are no points that are very close to one another, right? So if 2 points are very close to one another, they will be, one of them will be removed. Just evens out the distribution of points. Normal to density, this is a very important one. Normal to density actually changes, I guess. It actually changes the distribution of points. So how do I explain this? One second. Imagine a value, right? Imagine a value between 0 and 1. And all of the points that are on the landscape that have, let's say, all of the points that are around this area of the landscape that are basically pointing upwards have a value with them associated of 1. All of the points that are on this side, let's say on the side of the cliff in the landscape, that are pointing 90 degrees from upwards anywhere to any direction, but 90 degrees away from upwards that are horizontal, pointing in a horizontal direction, have a value of 0. That is what normal to density means. It associates the normal vector of the landscape of where the point is located with a value between 0 and 1, right? Then I give it a little bit of noise so that it's not very, clear cut of where we will draw the line of one asset needs to be used over the other asset. So I give it a noise of 0.1 from minus 0.1 to 0.1, and then we introduce a density filter. And I say that densities that are between 0.1 and 1 should use the fern leaves, and densities that are between, let me guess, 0.2 and 1 should use the rocks. That's weird. Lower bound, upper bound, 0.2 and 1. Oh, sorry, 0.1 and 1 is inverted. The filter is inverted. Right. So if it wasn't inverted, then everything would be right on the cliff. So if it's inverted, then everything is on the flat ground. I know that it's my explanation here is not that clear, but I'm not really keen on explaining how to place ferns. I'm going to be much more keen on explaining how to place architecture. Basically, we are driving the normal vector, or with the normal vector, we're driving which asset will be placed. Then we're transforming the points, giving them a little bit of random rotation and random scale. And thus, afterwards, we are just spawning mesh entities randomly on those points. And here I have, for the horizontal ones, I am spawning ferns, 6 different types of ferns. And for the vertical ones, I am spawning 5 different types of rocks. Okay, that's PCG generator in a nutshell. There are more functions. You can make a lot of crazy crap with it. It's a powerful tool, and that got me thinking. Let's open up an Unreal Engine 5 project. Don't save. Let's go for, or actually, before we open up PCG aggregate project, let's open up capsule 3DM 7 capsule 3DM file. And also, let's open up 7 for PCG Rhino file. So 2 Rhino files need to be opened. Again, Rhino 8 is loading in. Well, fine. I'll show this in Rhino 8, one of these files in Rhino 8, and the other one you will, we will work with the other one. It seems like I'm getting a little bit tired. It is what it is. Okay, so first of all, I guess the capsule. Let's talk about the capsule. This is going to be the element with which we will work, with which we will, just check out the system and how it works, how things align, and so on. My favorite, Nakagan Capsules Towers capsule. It's a mesh, and I have modeled it to high detail for the purpose of seeing how fast the PCG workflow is compared to the Excel spreadsheet workflow. So in total, this mesh has 1/3 polygons, 333,000 polygons. And you can see that this mesh that I have here is also rotated. And it's not just rotated randomly, it's actually rotated so that the door, middle of the door is on the 0, axis, or not axis, but 0, coordinate. And also it's aligned with the Z axis. That is because PCG, the way PCG system works, it really likes when the objects are placed around their Z axis. So Z axis becomes important, very important. So I export this this capsule by simply placing it here, selecting it, typing in the export, FBX file, blah, blah, blah. You know the drill. We already have it. We already have it in the folder. I have exported it for you, and it's called capsule.fbx. That's the one that we're going to be using. You don't need to export it yourselves. That's fine. That's it about the capsule. I guess I can. Unfortunately, this building that had this interior, these capsules, has been recently demolished, and one of my passion projects that I'm working on, and I am in hopes of finishing it by the end of this year or next year at the latest, is a revival of the Nakakin Capsule Tower in virtual reality. So I am working on creating a virtual reality space where you can experience the Nakakin Capsule Tower and it's at its fullest, and I'll of course associate some sort of a storytelling element and so on with it, right? So we will build up the whole damn thing and you'll be able to walk around in it. So stay tuned, you know, if I can see that Michael is uh, constantly showing follow Gediminas on Instagram in the chat. So the moment I'm finished with the Nakakin Capsule Towers VR experience, I will share it on Instagram, and it's going to be, for sure, it's going to be free for anyone to use, connect, and long-term plan is to have it online as well, so that as you have your headset on, you can, you know, VR chat style, you can meet up with other people inside. But as it is right now, it's going to be a standalone virtual reality experience with some storytelling elements. That was not a marketing thing, by the way. This was just, I really like the Nakakin Capsule Tower. Sorry. Moving on. Let me just close this so that we don't talk about it more. Moving on. So 7.4 PCG Rhino file, and let's type in Grasshopper and load in the 7.4 PCG Grasshopper file as well. I'll explain what are these triangles that you see and what the hell is going on. That is not the one. There we go. Drag and drop in. All good? All good. A very small script. Okay, so remember the random distribution, distribution on a mesh that I was talking about, the Poisson sampling on a mesh. There's other types of sampling, and one of them is called triangular sampling or triangle sampling. Basically, the way PCG works, it can take a mesh and it can place a single object on each of the faces or triangles of a mesh. It can be done. So what we need to do is, instead of points, we can just construct triangles, right? And this is what the script does. We construct a form, not a form, sorry. We construct a grid or an arrangement of triangles to which our Nakagen capsules for the Nakagen capsule tower will be anchored, right? Let me guide you through this real quick. I create a bounding box or a box. The size of the box is the size of the capsule, right? Because I want to work of that capsule that we're using, because I want to work, you know, with them as if they're bricks almost. I array them 20 by 20 by 20, a lot, large. I create a surface. In this case, you know, there's different ways of how to make it, but I create this arched, weird, or simple, I guess, surface. And I check for collisions between the boxes and the surface. And I get my answers. And according to the answers that I got, I eliminate all of the boxes that are not colliding with the surface, leaving only the ones that are. Then I get the middle point, right? Let me check one thing. Okay. You will need a Fox plugin for this. Damn it. Me being me, I forget. Special folders, components folder, Fox. We only need aggregations, honestly, for this to work, I guess. Or graph. Okay, I'll just give you the GHA files. The DLL files are not necessary in this case. And I guess I can just give it to you in this, in the chat. So this is going to be a little bit easier since these are GHA files. You can just drag and drop them into the Grasshopper window, and they will just simply load in. If it complains, ignore it. just let it load in, and they will be available. You won't need to restart Grasshopper. Another thing is, if you have already loaded in this Grasshopper script, then this part might be a white rectangle for you. So just create, after you have dragged and dropped in the aggregations as well as Grasshopper graph GHA files, make sure to just rotate plane by axis, connect plane to the P input to the rotate plane input, and the axis should not be X, it should be Y. So //Y, enter, and connect that to the axis. And then you're good to go, right? Whoopsie. Moving on. So back here, I get the plane, but the plane is horizontal. I don't want it to be horizontal. I rotate it around the y-axis by 90 degrees. 90 is the default degrees. By its own y-axis, and then I get the freaking vertical plane. Then I also, what I do is I rotate the plane 90 degrees. Don't remember why I did that, but clearly important. 90 degrees around its z-axis. So it's flipped vertical and then rotated by 90 degrees around its z-axis. I deconstruct the plane. To get its origin point. So I get point number 0. Let me find one of the triangles. Actually hide the triangle. Hide the triangles. So I get, as as I deconstruct the plane, I get point 0, which is its origin. Then I move that point along the x axis of the plane by 100 centimeters by 1 meter. And also I move it along the y axis of the plane by 100 centimeters, right? I get 3 points. I merge them, first one, second one, third one, and I construct a mesh from them, right? So I could basically construct a triangle from point 0, 1, and 2. And then I just join all of the triangles together, you know, into one big happy triangle family. So we voxelize, well, it's not really voxelization, but we kind of voxelize. We compartmentalize is that a word? No, it's not a word. I'm just inventing words. We elementize the space. We divide up the space into the segments that are as large as our Nakagen capsule tower's capsule. And for each point of the capsule, we create a plane. And then in that plane, we create a triangle. And then we join all of those triangles up, show, into a triangular mesh, right? And I also have this mesh exported for you as well. So you should see it, testerbase.fbx. Okay, now we go to our PCG aggregate, 8 PCG aggregate, and we open up this Unreal Engine 5 project. It's going to be very, very much empty. We will be creating our own little Nakagen capsule tower bridge thing, weird thing. Okay. I'll give you a moment. While you are loading in the Unreal Engine 5 project, I want to mention that PCG function or PCG tool, PCG tool, is not available by default in Unreal Engine 5.3.2. To make it available, you need to go to Settings, Plugins, type in PCG, Settings and Plugins, left-hand side, right-hand side, top right-hand side, Settings, click Plugins, click, type in PCG, and here you will have 3 tick marks to tick mark. Procedural content generation framework, right? You tick mark these 3, it's gonna yell at you to restart, you restart, you're good to go. I'm not sure if the file that I have sent you also comes with the PCG plugin enabled or if you need to enable it yourself. So if you see tick marks already tick marked, that means you're good to go, right? If you don't tick mark them, restart Unreal Engine 5 project, and then you're good to go. Okay. I have created for you a new level that is absolutely empty, completely empty. So the first thing that we want to do in this level is create some light. Let there be light, an environment, right? Well, no floor, but just light. Very easy to do. Thank God for environment light mixer. You go to Window, top window, environment light mixer. Click on that. Opens up a new tab for you. Expand it a little bit. Click on Create Skylight. Click on Create Atmospheric Light. Click on Create Sky Atmosphere. Click on Create Volumetric Cloud. Click on Create Height Fog. Close Environment Light Mixer. Congratulations, you have a fully working environment, right? With the clouds and animated and so on. Never been so easy. Very, very nice tool to have. moving on. Now it's time for us to actually create, first let's import stuff. I think importing our triangles as well as our capsule is important. So let's go to PCG, folder, bottom left, content drawer, PCG, expand, geometry. We're going to get both of our objects, FBX files, in here. Perfect. In my folder, design morphine, I have capsule.fbx. I drag and drop it in. Asks me, should it build nanite from it? I agree. And I just hit on import. Okay, I forgot to remove the leather. That's fine. That's fine. So the capsule will look weird for a little bit. Don't worry about it. We will fix it. We'll fix it. Because it's made out of leather right now without any texture mapping information. Okay, so that the capsule is imported. It complains a little bit for us with the message log. We ignore it. That's fine. It's not the cleanest mesh out there. And then we import the tester base.fbx as well. Drag and drop that in. Same folder, geometry, same folder. Import. Okay, close, close. Now what we have is a normal map. That's for the letter. Capsule, static mesh. Tester base, static mesh, leather material, and material 2 material. We will not need the leather material. We will only be using material 2 because it's nice and is it white? Yeah, it's nice and white. So sure, let's just use it. And also, honestly, let's just click on, double click on material 2. Choose the param here, the one with the white color, the param node. And for the default value of it, click on the white color and just drop it down just a little bit so that it's not full white, but like 90% white, right? Or 85. Hit save, close it, you're good to go. For the leather material, I will just hit delete, force delete. For the texture, I will just hit delete. For the normal texture, delete, don't need it. I'll open up the capsule, my static mesh. I'll look at it. Horrible, horrible. And that is what happens when you don't do UV mapping. This tutorial or this webinar does not require us to do UV mapping for the capsule, so I skipped it. Let's, instead of using world grid material here for the capsule, let's actually drag and drop in, open up the content drawer, drag and drop in material 2 for it. See, all of our war crimes have been hidden. I also will, while we're here, we'll go to fallback target. Instead of auto, change it to relative error. And fallback relative error, I'll change it to 0. Apply. Okay. Save. Close. If I drag and drop in my capsule now into the scene, I kind of want to rotate it like that and that. You know, pretty decent. And with Control L, remember, we can drive the light and we can take a look at how the light interacts with the, you know, with this mesh. And it doesn't seem like nanite, or sorry, that lumen is freaking out too much. Just give me one quick second. I will just check. That's actually, there are, oh, okay. There are places where Lumen is freaking out and does not like us as much, but I think most of these are fine. And yeah, like leaking happens. So you can see that since Lumen is freaking out in this particular corner, it only uses screen space shading, screen space shadowing. So on the edge of our screen, light leaking happens, which is fine. And for instance, this corner does not have that problem because that's where Lumen was actually working pretty well. I think we're good. I think we're good, and our capsule is ready to go. Okay, let me. Actually, we don't need it, so I'll just delete it. In terms of tester base, if I drag and drop it in, very confused. Hello? Should be. Oh, I know what's happening. Okay, it's inside out. It's inside out. So what we can do is actually still double click on the material. And here choose two-sided. On the left-hand side, two-sided in the options. Click Save. Close. Content drawer. Tester base. Now it should display. Oh no. Is that one of the... I'm a little bit confused, a little bit scared, but it seems like at least the preview of it is working. And it is here. It's just not really displaying it to us in the Unreal Engine 5, like in the scene, which is fine. We don't need to see it. It's just, I'm confused why it's not showing it. That's fine. If it's gonna be a problem, then we'll fix it. For now, we move on. We have our capsule. The capsule needs to be placed on the triangles. In the PCG folder, in the main one, PCG, right click, choose PCG, PCG graph. Call it my first PCG. Double click it, opens up the graph for you. Okay. Remember the mesh sample, spawn mesh, blah, 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 all of that chain? We don't need that whole chain. We need only few things. Ironically, we don't really need input and output. We just work without these because these don't do anything to us. Because we don't even have a landscape in this scene, so it, there's nothing. First node that we create in our PCG is going to be called mesh sampler. Oh yeah, you can you can right click anywhere on the empty scene, empty space, and you type in mesh sampler. Bam, that's the one. As you select this node, it asks you to give it, what's the mesh and how would you sample it. And you can see if I expand this, there's 1 point per triangle, 1 point per vertex, Poisson sampling, right? And we are going to be using 1 point per triangle. There we go. Because we have triangles for each place where the towers capsules should be placed. Static mesh, we just drag and drop in. Content drawer, open that one up, go to geometry. You have your tester base. Tester base, that is going to be what is going to be sampled, basically, right? So that's done, and we don't need to do anything else with this. Already for each triangle of the tester base, of these triangles is going to create one point, one entity. Then what we want to do is mesh spawner. Oh, sorry, static mesh spawner. Same thing. Static mesh spawner. We connect our mesh sampler to static mesh spawner, like so. And as we select this node here, we need to actually specify what kind of entities or meshes should be spawned, right? So here under mesh entries, I click on this little plus sign, add element, which adds an index 0 element. I expand it. Make sure that you have static mesh spawner selected, or else you won't see the menu. I expand this index 1. There's a descriptor. I expand this, and here we have everything about the mesh that is going to be placed, right? Honestly, most of it I just keep as default. You could change this to static instead of movable, but even that does not really matter as much. And here for the static mesh, I just drag and drop in the capsule like that. Save. For now, let's just drag it somewhere to the side. That's fine. Or actually, I'll just drag it as a new tab next to my level, like so. Okay. Now back in the content drawer, PCG. All you need to do for it to work now, hopefully, fingers crossed, is you just drag and drop it in like that. Typical. Please work. Oh, there it is. Okay. Thank God. Thank God. I got scared there for a second. Okay. So here it is, right? A few things to note. Quite a few things to note, actually. Thing number one is the PCG. This little box here, that is my first PCG thing. If I were to move it to the side, you can see that everything moves, right? No. If I move it and I release the mouse key, the boxes or the capsules snap to the initial place. Do you know where those are? That is exactly where those triangles were created in the first place at 0, 0, 0, from 0, 0, 0, right? So it's always going to sample this mesh according to the 0, 0, 0 position. If you want to move it to a different position, you can, but that would require you to add more nodes in the PCG spawner itself. Second thing is, if I were to look at the doors, well, that's rotated, right? So all of the capsules are rotated horizontally 90 degrees. We need to fix that. So back in here, back in our PCG, if you closed it, you go to content drawer, you just double click on it again, open it up. Between the mesh sampler and the static mesh spawner, we will be using one more node that is going to be called something transform. Oh no, yeah, transform points, thank God. Transform points, that one. Bam. Holding the control key or alt key, I don't remember, disconnect the static mesh spawner from the mesh sampler and instead have transform points in between them, like that. Now, these transform points, if I select this, you can add random rotations to these. For this, we need to see. For this, we really want to want to see how this will work. So I'm going to kind of position this a little bit like that, I guess. Yeah, something like this. Okay. Rotation minimum, rotation maximum. Let's go for rotation minimum around x-axis minus 10 degrees. Maximum 10 degrees. Each block is rotated by a random value of minus 10 to 10. That's not something that we want in this case, so we keep it as 0. The values that we want to rotate are around the z-axis, right? So we can do, oops, minus 90 and rotation maximum minus 90. If both of these match up, all of the elements will be rotated exactly by minus 90 degrees, right? And now they are all looking in the correct orientation, or yeah, they're oriented correctly, right? And now I can go through them just like so. I want to note that, it's a lot of polygons yet again, right? We look at it. That's quite a few polygons in this environment, and it's 120 frames per second. Yet again. And as I can control the light in real time, blah blah blah. You know the drill by now. All right, so that's one thing. We're getting close to the end of this webinar, but a few things. Just like the previous one, the Excel spreadsheet workflow, this one also lends itself to quick adjustments and quick changes. I will show that in just a second. Also, this lends itself to a little bit more human, or a little bit less machinic approach in terms of how we stack things. So the transform points, you can jitter the values, 3 degrees, sorry, from minus 3 until 3 degrees. This is very extreme, but you understand what I mean. So let me do something very like minus 1, like 1 degree offset, or randomization for all of these. Looks like that. Oh, that's still too much. Apologies, I'm playing now, but I really want this to be pretty. 0.5. Yeah, okay. That's good, right? So some seams are intersecting, others are making a little bit more of a gap. It's not an equal, how do I say? The placement of them is not perfect, and I think that really, like, aesthetically, visually, that helps. Offset minimum minus 5 centimeters, offset maximum 5 centimeters for all of these. You just end up having this a little bit more organic placement of the elements. So that's one thing. Second thing, and I will end it with this, is how do you change up things and how do you transform things? This is actually very, very simple. If I were to just say, okay, I don't want to use this, but I will be using I wish I had like a duck mesh or something like that. But let's just switch to sphere. Why not? But a larger one, I guess. Just bear with me. Like that. That's the box array, sorry. Box array. Yoink. Oh, and this can be an ellipsoid then. Like that. Okay. Set one surface, that's the surface. Just give it a second to go through all of these and then calculate the intersections. Okay, it's done. You know, we have all of these triangles now. Inside as well, that's weird. It should be only around the surface. Well, whatever, we'll take it. So that's going to be the amount of copies of the neck again capsule that it's going to make. And I just insert it, export this FBX or motion builder, sorry, motion builder FBX, tester base, save, yes. Go back in here, content drawer, geometry, tester base, right click, re-import, calculates. Now we have like a weird Zeppelin thing. And notice how this, notice how this does not update, right? To force an update, I believe you need to regenerate it here. So you select the PCG and you click on generate, and then it should work. No, you click on cleanup, and then you click on generate. Still doesn't work, right? That's what I had to deal with as well in previous iterations of this workflow. You actually need to go to the PCG and you can't use the same seed for the mesh sampler as what you're using currently. I don't know why, but the current seed that is being used is already being used by the previously used triangular, you know, like this arch triangular shape thing. Sorry, the previous base. So what you need to do is just change the seed to any other value. And now as you change it, now I need to escape from here. I'm inside of the structure. Yeah, there we go. Now we're good to go. Now we're in this Nakagen capsule tower Zeppelin, right? So mesh sampler, changing the seed triggers a recalculation of, yeah, of the whole thing. I just want to note that it's, oops. There's a lot of meshes that all still, you know, work quite well without any hitches. So this is the current state of my, not research, but of what I'm working on. PCG is a powerful tool that can be quite a good alternative to the Excel spreadsheet methodology of exporting cells, I guess, colossal cells, if you will, exporting them from Rhino into Unreal Engine. Both are able to push a lot of polygons without any issues whatsoever. Both are quick to iterate through and to update as long as you're just re-importing and you know which you know triggers to press for the structure to update. And both have similar limitations. In case of PCG, the main limitation that I have noticed is currently, well, it's not even a limitation, it's just you need a chain of additional nodes for it to work. Is while here the windows are looking outwards, if I look at the opposite side, these are all doors. So all of the elements are looking outwards there. And I think that has something to do with the triangles, with the back face and front face of the triangles, but I haven't been able to see how consistent, the consistency at which the front face of the triangle dictates the positive z axis of the object. My hopes are that it's very consistent, and then we don't need to do a bunch of checks and so on. That would require a lot of computational power, and the chain of command would be, for PCG, would be much longer. So currently the PCG graph, a lot of talking for 3 nodes, but hopefully you understand how to operate with them. Okay. That is it. I guess we still have plenty of time for questions and answers. So if you have any questions, just shoot. I'll be happy to answer. Oh, it was my pleasure, Yolanda. And I assume
Thank you. It was awesome.
Oh, hi. I got so used to talking to myself.
Very good. Do you guys have any questions? If you do, let us know. If not, we will end this awesome webinar. It was a lot of fun.
Oh yeah, it's I expected it to crash more. Let me just say it like that. It didn't crash as much as I expected it to.
Well, that's always pleasant.
Yeah. That's I welcome that anytime.
Well, here, Alex has a question for you.
I'm curious about how you might go about converting complete aggregation in Unreal into some kind of single mesh. My main idea is about how to try and 3D print some really huge aggregations that slicers will struggle with while minimizing face count. That's a very good question, and that comes down to the slicer. Okay, yeah, I do have some thoughts on it. That comes down to the way slicers are constructed and the way they slice, right? They literally are creating coordinates for the movement of the tool head. So the moment you are trying to slice these multi-billion polygon meshes in the first place, you're not doing it correctly. I feel like that the best way of how to give instructions for slicing is to never leave Grasshopper in the first place, and have for each element. One second, thinking. Yes, okay, so the way I would do it is for each element, I would have a built-in, already pre-built curves that the tool should follow, a tool that would be printing it should follow. And the curves should, of course, rotate together with the element and align with the world XY axes, which is a little bit tricky to do, but as long as you're using blocks, that's doable. So you wouldn't be dealing with meshes or sub-D or anything for slicing. You would already be growing the structure together with embedded curves in the structure, right? Think of it this way: mesh plus curves in a block. Then what you do is you download the plugin for Grasshopper called Silkworm. I'm sure you're probably familiar with that. And you feed those curves into Silkworm. as tool paths. It's still going to be a very, very heavy, they're going to be very, very heavy, but I feel like at that point, it starts becoming doable because you're not dealing with actually converting a mesh into a bunch of slices. You already have the slices, and all you need to do is build the G code from them. Silkworm plugin will do that. Oh, another thing. Unfortunately, slicers are limited in this way if you're not using an FDM printer. If you want to use a Formlabs printer, for example, you must use their slicer, which won't integrate well with Grasshopper. Oh yeah. Don't. Just don't. Just use a printer that where you can feed. How do you say? Where you can feed custom G code or hack it. So I don't know if I can tell this. Probably I can. Who cares? In the university, in Lund University where I teach, we have this large scale WASP printer, which is Italian brand that they used to build really great printers. I'm not sure what they do these days. And the problem with the WASP printer is that we didn't have profiles for the WASP, for the printer itself. So what we ended up doing is completely hacking it and not replacing the motherboard on it, but enhancing, let's say, the motherboard on it so that it can just read raw G code without any checks for, is it sliced in the proper software and so on. And then we have, G code that is generated in Grasshopper just feeding into that 3D printer, right? So we kind of, the same problem that you have with the Formlabs printer, we solved it by breaking the printer that we had. And later down the line, literally breaking because some of the students, they didn't really create the cleanest G code. And I think one of the motors just overheated and now that printer is not serviceable. So I guess, how do I say? I guess those softwares that lock you in, or that's hardware that locks you into certain softwares has certain amounts of points, especially when it comes down to safety and so on. But honestly, I'm against hardware locking you into certain software. So I would just say, yeah, break it. There's no working around it otherwise.
Yeah. Okay. Well, guess that's it. Thank you everyone for joining and everyone that stayed the whole time. Thank you for doing this webinar. And
I had so much fun.
guess we can.
Okay. I'm out then.
All right.
Yeah, thanks everyone.
Thank you.
Yeah, thanks. Thank you. Bye guys.
See you everyone.